Good morning, students.
Good morning, sir.
Welcome to Physics Endgame. Alright, how's the journey been so far? Okay. Let the game begin. Today we are going to be studying quanta, which includes the particular nature of matter. The nucleus, we'll be doing nuclear chemistry, that is nuclear physics rather. The energy quantization, then wave particle duality. All right, but because of in day 4 we did not finish these guys, we're going to start with them. Is that okay? So basically in nuclear, in modern physics, these are the ones we have here. Is that okay? So, but this is other. This part is also under. Okay, it's under classical. Okay, it's under classical. All right. So these ones are under modern physics, as we said. Then this one, we're going to go from transformers where we stopped the last time and go up like this. We'll not pick it up from there again. Is that okay? Are you ready?
Yes, sir.
Let's go. Transformers. Now, what is a transformer? A transformer is any device that can be used to either increase voltage or what? Reduce voltage. So we have two types of transformer. We have the step-up transformer and the step-down. And the step-down transformer. Now, in a typical transformer, we basically have a soft iron core around which we have coils of wire on one end and coil of wire on the other end. Is that okay? And they are connected. We can be connected here or at the base. Okay? So this one is connected to the AC source. This one is connected to the what? The AC source, and this one is connected to the load. Yeah, these are bulb. Yeah, okay. So this one that is connected to the source, listen. So this is a typical transformer. This one that is connected to the source, this coil of wire that is connected to the source will be called the primary coil. Is that okay? Or primary turns. Is that okay? So the primary coil connected to the source, while the secondary coil is one that is connected to the load. Secondary coil. Now, for a step-up transformer, we have that the primary coil will be less than the number of turns or number of coils. The coils in the secondary part. In a step-up transformer, the number of turns of coil in the primary will be less than the one in the secondary. While in a step-down transformer, the number of coils in the primary or number of turns of coil in the primary will be more than the number of turns of coil in the secondary. So this one I drew now is what kind of coil? What kind of transformer are that? The step-down transformer, because the number of turns here is more than the number of turns that are going to the load. The number of turns on the other end that's going to the load. Is that okay? So when number of turns in primary is greater than number of turns in secondary, what would this be? Step down. So let's go SD. Step down transformer. Then when the number of turns in primary is less than the number of turns in secondary, what would that be? A step up transformer. Is this clear? All right. Now, how do we calculate the power in a transformer? Now recall that power is the amount of the amount of energy times time over time that we use. Is that okay? So the amount of power that this guy is dissipating, the transformer is dissipating, is calculated by as P equal to IV. Do you remember? Is that okay? But there are two sources here or two ends here. We have the primary and secondary. So the primary that is coming from the source is going to be calculated as power in primary coil is going to be I primary times what? Voltage in primary coil. Is that okay? Or you could see it as this, or current in primary coil times EMF in primary coil. Does this make sense? Then the one of the secondary will be power in secondary coil equal to IS times V sub S. Is that okay? Or you improvise with that too? Do we understand? Then the efficiency of this transformer can be calculated using efficiency is going to be what? What is going to be efficiency? Output, right? Over input times 100, right? Output over input times 100. So what is our output? Output is the one going to the load, right? Which is the what? Secondary. So we have so we say power PS over PP times 100 over 1. Does that make sense? So PS goes what? I sub S V sub S over I sub P V sub P times 100 over 1. Is this clear? So this is the formula for efficiency of transformer, and we're done with transformer. Are we good? Yes, we're done with transformer. We only need to solve questions on them now. So let's go to the next thing. The next thing I want to consider is the AC circuit. Somebody say AC circuit. Now, in a DC, you don't have to draw this again. I just want you to see this. I hope you know this guy is the same as this guy. Okay. Okay. So look at these two systems. Now, where's our DC system? Is it A or B?
A.
Which one is the direct current circuit here? A is the direct current circuit, right? Now, why is it called the direct current? It's called direct current because what? Current flows in what? One direction. And it's going to be from what? From positive to negative. And I've said this before. Direction of electron will have what? Negative to positive. Is that clear? Okay. So since current flows from positive to negative and in one direction, we call it DC circuit. Is that okay now? While this one is going to be the AC circuit. Why? If you look at here very well, you see something that looks like a wave, right? Yes, because it is made from oscillations. And what is the oscillation that is going on here? Current is moving from positive to negative and from negative to positive. Is that okay? So current is going back and forth in two directions. And that's why we call it what? Alternating current. It means it's alternating between highest values and lowest values. Highest value and lowest values. Albeit I said highest value and lowest value does not mean this is a low value. Where's the lowest value here? The point on this line. Do you understand now? The lowest value of these things, that whatever quantity is oscillating here, is going to be on this line. Is that okay? While the highest values, but in two different directions, are these crests and these what? Troughs. Okay? So we have considered wave. That shouldn't be a problem. So let's go right now. So it means that if it is oscillating between 2 points, it's going to have other characteristics of a wave, isn't it? It's going to have other things that we use to analyze or describe a wave, such as, for example, period. Does that make sense? It's going to have period of oscillation. It's going to have frequency of oscillation, isn't it? It's going to have phase difference. Do you get it now? All right. So it basically means that, and the reason it basically means that that the currents. Now, the two features first, that the two quantities that are oscillating there are what? The current and the voltage. Is that okay? The current and the voltage are moving between what? the positive to negative, negative to positive. Is that okay? No, not positive to negative, negative to positive. The positive and negative interchange direction. We've seen that in AC generators, isn't it? The positive and negative ends, they flip over, isn't it? So it's always positive to negative. But in the first instance, when it goes from positive to negative, by the time it goes again, the positive would have changed position. Is that okay? So that to go back from positive again to negative in the other end. Does it make sense? Okay. So if you don't understand what I said, raise your hand. Okay. So now that is about alternating currents. So if those two are oscillating between 2 points, then we can have a sinusoidal graph. Okay. So we're going to have something that looks like this. So our waveform of the voltage and current is represented in this way. Is that okay? So this highest value, or this point, or this point and this point are our highest values. Is that okay? So for voltage, it's going to be V maximum or V naught, or we call it peak voltage. We call it what?
Peak voltage.
Or maximum voltage. So you can see V sub M. Is that okay? Anyone you decide to use. So, but what if I wanted to calculate the current or voltage at a particular time? So if I want to calculate the current or voltage at a particular time, we'll call it instantaneous. What do I call it?
Instantaneous.
What would that be? Instantaneous voltage. Is that okay? Good. Now, do you remember that we said, so big voltage, V sub naught, instantaneous voltage, what? V at a particular time. Is that okay? Or in some textbooks you might see V sub T. Instantaneous means voltage at a particular time, at a specific time. Okay? So I want to use V, just V here, so that there will be no confusion as per the conventions. So then we now have what is also called the RMS value. I'm going to tell you what RMS value means. But before we do that, now let me show you how we calculate the instantaneous value or voltage at a particular time. As in, what this means is that since this voltage is rising to a particular level to its maximum and going back to its maximum, going to its maximum, coming back to the zero, going to the maximum, coming back to zero. Is that okay? If it's so, then it means that at a particular time, there was a time when very almost incalculable, but we know that. And that's what we want to do in the calculations. That we want to try and calculate it. So we know that there is a time when it will be here. So the voltage at this point, if the maximum level of voltage that is getting there is 250 volts, for example, there was a time, if it's oscillating between 250 and 0, it means that there was a time that we probably cannot measure that is actually 200. Does that make sense? Do you get it now? So that's what we call the instantaneous voltage. Is it clear? Okay. I've showed you that in wave, you want to calculate the vertical displacement is equal to what? A sine theta, yeah? Okay, so we can adopt this equation. A is also what? Amplitude, which corresponds to what? The peak voltage here. Does that make sense? So we can easily say, therefore, that our instantaneous voltage will be equal to the peak voltage sine theta. Does this make sense? Okay, so let's call this our equation 1. We're going to be generating a number of equations here. So, and we know that theta is equal to omega t. Does that make sense? So, instantaneous voltage will be V naught sine omega t. This makes sense, yeah? Isn't it? We can also have that. No, let's not bring all. Let's just go one more step. That V naught what? Sine 2 pi f t. So these are the possible values that we can have for our what? Our instantaneous voltage, or possible formulas rather that we can have for our instantaneous voltage. So if voltage is oscillating, we said it makes sense to say that current is also what? Oscillating. So in like manner, we are going to have instantaneous current, peak current. So the peak current or maximum current is going to be what? I sub naught. Is that okay? Which is this point 2 on if we change the graph to current graph. Is that okay? So we have instantaneous current. Instantaneous current. I. So I will be equal to what? I sub naught sine theta. So that I will be equal to what? I sub naught sine omega t. Does this make sense? Then I will be equal to I sub naught sine 2 pi f t. This makes sense, right? Okay. Okay. All right. Since we have this set of equations now, let's go to what is called the root mean square values. Now, this is it. Since this guy is oscillating between highest and minimum value, lowest and minimum, maximum and minimum values, it is not the maximum value of the voltage that is effective in that system, in that circuit. That is, the circuit is not exactly using the maximum value. Does that make sense? You know that if we neglect internal resistance and I connect a 12 volt battery to my direct current, that 12 volt battery should be the amount of joules of energy that will be transferred in the circuit. Does that make sense? Or the amount of energy that will be lost as heat in the resistor. Does that make sense? Okay, that is in a direct current. But in an alternating current, because the guy is oscillating between maximum and minimum value, we cannot use the maximum value to estimate the amount of voltage that that system is using. Is that okay? So the amount of voltage that is effective in that system is what we call the root mean squared value. Is what we call what? So in your textbook you might see a definition that says that the root mean squared value is the amount of maybe voltage, for example. If it's root mean squared voltage, RMS voltage is the amount of voltage that will dissipate. No, root mean squared current. That's one I think I remember. Amount of current that will dissipate as much heat as would a DC or so. What that means is just that if your circuit were to be running like a DC, what is the amount of voltage that it uses up? Does that make sense now? Okay, so that will be our root mean squared. So for voltage, we'll call it VRMS. Is that okay? So VRMS is going to be given by the peak value of that voltage over root 2. Does this make sense? And by the time you solve 1 over root 2, you discover that root mean squared value is equal to 0.7071 or so V sub naught. Is that okay? So if you do this, you are going to get your root mean squared value. That's for voltage. How about for current? So IRMS will be the same I sub naught over what? Root 2. Does that make sense? So VIRMS therefore we got what? I naught times 0.707 I naught. Is that okay? Good. Now, in an AC circuit, we also have components that we normally connect just like the DC. But the reason why we study them differently now is that the reactions are quite the same than in a direct current circuit. In a direct current circuit, you know all energy will be lost at resistance, current to flow back to take up energy and then flow again. Do you understand? And that loop will continue like that, right? But in this case, there are other components that we attach to the system, such as the inductor, such as the capacitor, and we always connect them in series. Is that okay? So when we connect them in series, they have an impact they play on the amount of voltage that runs in the system. Does that make sense? Are you with me?
Yes, sir.
Okay. So we are going to first consider a case where, so we can either connect an inductor alone to the system, we call it to the circuit, we call it a purely inductive circuit. If we connect a capacitor alone, we'll call it a purely capacitive circuit. Is that okay? And if we connected a resistance alone, a resistor alone rather, we'll call it a purely resistive circuit. Does that make sense? Now we can now begin to make different alternations or different combinations rather. We can combine inductor and capacitor, combine capacitor and resistor, inductor and resistor, or the three. Is that clear? And we're going to be generating. The problem with AC is it has many formulas, but the easy thing is that all the formulas are linked. All the formulas are what? They are linked to one another. So let's go now. Let's start with the purely resistive circuit. So purely resistive. When you hear polyresistive, what will be there? What will be the only component there? Resistor. So we'll have something that looks like this. So the only thing that is consuming power here is our resistor. Does that make sense? So, and it's connected in series to the source. Is that okay? So in this case, in this condition, because it is a purely resistive circuit, voltage and current are in phase. Voltage and current are what?
Phase.
Are in phase means that they flow together. Is that okay? Think of it as they flow together. Do you get it? Not one is lagging behind the other. So in a purely resistive circuit, only resistance. The moment you switch on the light, you see this thing attains its maximum immediately. The load attains its maximum immediately. Do you get it? Okay. Now, so in this case, if that's what happens, then it means our calculations are just as normal. V will be equal to what? IR. Does this make sense? We know this, right?
Yes, sir.
So the voltage that will run in this system is going to be V equals IR. Since we said that current and voltage are in phase. Is that okay? And if they are in phase, it means they are working together. So any of these graphs can be used to represent it. Since they are in phase, we are going to have something like this. So this will be either the current and voltage or current, voltage and current. Is that okay? They are in phase. They are in the same phase. Means of the 360-degree cycle. It means they are on the same position. They are at the same position at a given time. Is that okay? All right. When we get to the next condition, now you see why we study, why we talk about phase difference. You understand? Okay. So if you want to calculate power too, and I mean what this means is that peak voltage here will be equal to what? Peak current times resistance. RMS voltage here will be what? IRMS times resistance. Is this clear? Okay. So those are the major things you calculate. Power there too. Power is going to what? IV. Is this clear? Okay. Now, what if we have a purely inductive circuit? Now, a purely inductive circuit is one that has only the inductor connected in series with the voltage. Is that okay? So we have inductor. There's our inductor. What's the symbol for our inductor? Something like this, right? It's connected in series to the voltage source. So it's purely inductive. Now this is what happens. Let me first change this to a direct current. You're going to see what you mean now. In a direct current, the moment you connect, you switch this system on, current begins to flow in this direction. Here's what happens. If there was a load that's connected across this thing, what you will see is this. If it was a bulb, you will notice that the bulb will not glow to its brightest immediately. The moment you connect the key, the switch is on, what will happen is that this thing will begin to increase in its intensity until after a while when the current has reached its maximum value. Is that okay? Yeah. So for me to even say current has reached its maximum value, you already know which one is lagging behind, right? Isn't it? Okay. So that's for the case of this. And the reason is because this guy has an opposition to the flow of current, or offers an opposition to the flow of current, that is called inductive reactance. So now let's talk about reactance first. So reactance given by X, is denoted by X, is the opposition to the flow of current that is offered by either a capacitor or an inductor. So in this case, it's going to be by an inductor, so we'll call it inductive reactance. We call it what?
Inductive reactance.
Okay. I said reactance is the opposition offered by inductor or capacitor or both of them alone. Once there is resistor there, it becomes impedance. It becomes what? Or impedance, actually. It's not impedance, impedance. Okay, so my point is this. So these are our AC source, and then, so This guy is going to offer an opposition called inductive reactance. We denote it by X sub L. Is that okay? So we have that X sub L is going to be equal to what? Omega L. Now what is L? Our inductance. Our L is what? Inductance. You'll be given your inductance. So X sub L is your inductive reactance. Inductive reactance. So in omega L, then we have that X sub L. What's omega? That's 2 pi F L. Does this make sense? So this is the formula for inductive reactance. Are we good? So the voltage that now flows across this inductor, we'll call it V sub L, is going to be I times X sub L. Does this make sense? I times what? X sub L. X sub L being the what? Inductive reactance. Are we good with that? Okay. Now, in a purely inductive circuit, I showed you that since we use this thing to represent inductance, this letter L to represent inductance, just turn it by some degrees. It's going to turn to V, right? So, this one, voltage is the leader. Is that okay? Who leads? Voltage. So that's why if it were a condition of good morning, ma. Yes, ma. Yes, ma. If it were a condition of this thing, what's it called? DC, it will take some time for that guy to reach his maximum brightness, right? Or for the maximum current to flow. Remember we said that this guy offers opposition to the flow of current, right? And we said it was because of changing what? Magnetic flux, isn't it? Why is it changing magnetic flux? Current is changing, isn't it? So a changing magnetic flux also induces eddy current. Is that okay? Okay. So that's why current will lag behind. Current will do what? Lag behind. So current will be out of phase, or current and voltage will be out of phase by 90 degrees. Is that okay? And who will be the leader? Voltage. So voltage will lead current by 90 degrees, or current will lag voltage by 90 degrees. So that it means that if voltage in this guy is I and is V naught, if voltage in this guy is V naught, that is instantaneous voltage through the guy, is V naught, what's the formula again? V naught sine 2 pi ft. That was the formula we generated, right? Is that okay? But let's just use omega. It's the same, is that okay? V naught sine omega t. If this is our instantaneous voltage here, it means that since voltage is the leader here, if you relate voltage and current will be the one to have current in this circuit is going to be, so we might not put V sub L, we might just put V or I. Is that okay? Okay. But we'll put V sub L to show you that it is the one across here. Does that make sense? So I will be equal to I naught sine, now listen, omega t plus what? 90 gram naught. Now who is leading? Voltage is leading, right? So this one should be plus 90 gram naught. Do you understand now? Okay. So in this case, it means that our formula will become V will be equal to V sub naught sine omega t plus what is 90 gram naught? Pi over 4. Does this make sense? So this will be the equation for V in this circuit. Why? Because this guy is leading by 90 degrees. If this guy is I naught sine omega t, then this one should be V naught sine omega t plus 90 degrees. Is that okay? Or if in a case where V is V naught sine omega t, then I should be what? I naught sine omega t minus, God bless you. Does that make sense now? Does that make sense? Okay. So these are the possible formulas that you can generate for that guy. Now, so remember that in a purely inductive, voltage leads by 90 degrees or current lags by 90 degrees. Okay, so in a purely capacitive circuit now, in a purely capacitive circuit, the only components we have there is what? The capacitor. This guy represents capacitor, right? Parallel plates. Do you remember? Okay, so we have that in a purely capacitive circuit, that capacitor will also offer opposition to the flow of current, known as what? Capacitive reactance. I will call it X sub C. So X sub C is given by the formula 1 over omega C. Does this make sense? So X of C is equal to 1 over 2 pi FC. Why is it looking new, like I've not taught it before? I've taught it before now. Looking like it's been long I wrote it. Okay, so 1 over 2 pi FC. Now, so if you want to calculate the voltage across the capacitor, what is that going to give us? Oh, I didn't show you the graph for this. Now, the graph for this guy. So this way we show the sine graph. Who is leading here? Voltage, right? So let me show you two graphs now. The window is not so correct. Which one do you think will be this waveform A and waveform B? Which one do you think will be the voltage and which one do you think will be the current? B will be what? Voltage. That's correct. Because if you look at it, this one, by the time it's attaining its minimum value, this one is attaining is what? Maximum value. Are you with me? Do you get what I'm saying? So this guy is the leader. So this guy will be the volt. No, A is voltage. A is voltage now. A is voltage. Waveform A is here now. Do you get it? And waveform B is here. Is that clear? So waveform B will be current, waveform A will be voltage. Do you understand? Is it confusing? The one that is confusing. The one that starts from here is the one that is lagging now. You know? This one is starting from the top here. So it means that by the time this guy, if they move at the same time, if they move at the same time, this one would have attained maximum value. This one is attaining minimum value. It's just going to attain it. Do you understand now? So that's the leader. The voltage is the leader. The current is here. So we say that the voltage is going to be leading, right? Voltage is leading, and current is lagging. How do we represent that? Who is leading here? They'll be in phase. They'll have a phase difference. Since voltage is leading, voltage will be here, current will be here. Does this make sense? They will lag by how many degrees? 90 degrees. Voltage, current. Is that clear? Okay, you've seen this kind of graph before, okay? Do you understand? All right. Now, V sub C here is going to be what? Current times X sub C. Although almost like, you know, there are forms of resistance. Is that okay? Only that they are not exactly from the resistor itself. So that's how we use different letters to represent them. Now, so in this case also, if V here is V naught sine omega t, what will current be here? Which one will lag behind here? Or which one will lead? Just use the same trick here, because we said L, which is inductance, can be written like V. So voltage is leading. So here capacitor is C, right? So current will what? Will lead. Is that okay? That trick is for the leaders, so you know the laggers. So this guy is leading, current is leading voltage by how many degrees still? 90 degrees. Is that okay? And why is the leading happening? Because these capacitors will first store up some voltage before allowing the remaining to pass through. Is that okay? So by storing up that voltage is causing a lag in the voltage. Do Do you understand? All right. So we have current will be equal to what? I sub naught sine omega t. Who is leading? Current is leading. So it will be what? Plus. Does that make sense? Or if this one were to be I equal to I sub naught sine omega t, what would this one be? Minus pi over 4. Is that clear? All right. So that is the case. Now, what we now have a circuit where both are combined. So let's combine both now. Have you written these topics? Okay, so what if we now combine a capacitor and an inductor? So we call that an LC circuit. We call it what?
LC circuit.
Okay, in an LC circuit, we're going to have the two components L and C. Okay, so we have our L, inductor, here, capacitor. Now in this case, are you listening to me?
Yes, sir.
Opposition will be offered by both what? Capacitor and what? Inductor. Opposition will be offered by what? An inductor. So, and the opposition is called reactance now. Reactance X. So X here is given by X sub L minus X sub C. Is this clear? Now, it therefore means that the voltage here, V sub, just V here, will be equal to what? I times X sub I times X. Does this make sense? Is this clear? Okay. So if this is the case, then we can say that voltage is what? I into bracket X sub L times minus X sub C. Does this make sense here? Okay. Now, the other type of circuit we can now have is the RL circuit. In an RL circuit, what and what do we have connected? The resistor and what? Inductor. Now, whenever you have resistor with another component, we have an opposition called impedance. Is that okay? Impedance. So let me draw that here. Let's say RL circuit. Okay, it's already here. So let's just connect. So we have the RL. In the RL circuit, we have our resistor here, and then we have this is our L. So in this case, opposition will be termed impedance, like we said, and the impedance is denoted by Z. Is that okay? So, and Z here, Z in this case is going to be Z squared, or you say is the square root, or is the same, or is that okay? It's the square root, or let me write it that way so that you know that it's just by Pythagoras rule. So Z squared is going to be the resistance squared plus X sub L squared. Does this make sense? So that Z will be equal to the square root of R squared plus X sub L. Is this clear? So the voltage here is going to be I times Z squared. Okay. Is this clear? Okay. So, okay, we've not even been considering the power so far. Because in this case, there's something called the power factor. There's something called what? Power factor. Now, so power here is calculated as IZ cos phi. It's calculated as what?
IZ cos phi.
So now, that phi is known as power factor. No, cos phi, not phi. Cos phi is known as what? Power factor. And cos phi is giving us the ratio of, is it Z over resistance or resistance over Z? Resistance over Z. Do we get it? So by the time you take the ratio, you are going to get the cos phi is an angle too. Is that okay? All right. The other formula we need is in an RC circuit. We've seen like two more. RC and RLC. We now combine everything. Now, in an RC circuit, we have the resistor and the capacitor. Okay, RC. So the opposition will also be called what? Impedance. And that impedance still will be calculated as what? The square root of what? R squared plus X sub C squared. Thank you. Are you with me? Okay. I didn't mention the voltage here. I forgot to mention that. You can also say that the voltage here is also equal to, just substitute this guy. Do you understand? I mean, in your calculation, you can first find the impedance, then multiply this. Is that okay? Because if you have seen some formulas like this in your textbook, V over maybe square root of R square, all those things. And it's just saying I will be what? V over Z, since Z is already this. Does this make sense? Okay, let's go on. So here, the impedance here is going to be square root of all of this. And then the voltage here is going to be what? IZ also. Is this clear? Okay. Okay. Power factor the same way. Power factor the same way. Alright. Now, what if we now have an RLC circuit? Now, in an RLC circuit, we have the resistor, the inductor, and the capacitor. Resistor, inductor, capacitor. RLC. So in this type of this thing, opposition is still what? Impedance. And here impedance is now equal to what? The square root of R squared here plus X of L minus X of C all squared. Do you understand? Remember that this will be what? X, these two together. X, right? So it means we can revise our equation as what? Z equal to what? Square root of R squared plus X squared. Do you understand? Do we get it? So our voltage here is going to be what? Still IZ. Are we clear? So all the voltages, now this voltage we are calculating so far, they are instantaneous. So is that okay? So because we are looking for root mean square value, it will be VRMS equal to what? IRMS times Z. Do you not get that? If it's peak value to what? V naught equals so we now have this. So this is the case of RLC circuit. Now the last part which we will consider under the AC is the condition of resonance. Is that okay? The condition of resonance. Now there's a common question that they ask about condition of resonance too, and it's about the application. One of the very common application of resonance is in metal detectors. That metal detector that is to set your body. Is that okay? It works by resonance. Is that okay? All right. So I said that condition of what? Resonance. So condition of resonance occurs when the X sub L is exactly equal to what? X sub C. And if this is the case, at what frequency does that happen? That frequency at which this happens is called the resonant frequency. The frequency at which X sub L is equal to X sub C is called what? Resonance frequency. So since this one is already omega L and this one is 1 over omega C, and we have 2 pi FL is equal to 1 over 2 pi FC. Okay? By the time you do your cross multiplication, we have, I know we have derived this so many times, right? 4 pi squared F squared LC. Right? Want to make F subject, we divide both sides by 4 pi squared LC. Want to make F subject. This goes, we'll be left, this one will come in. This whole thing will come in, right? So f squared will be equal to 1 over 4 pi squared LC. So you now take square root of both sides, and you have f will be equal to what?
1 over.
Square root of 1 over, oh no, if you take square root of 1, it's what? 1. Square root of 4, 2. Square root of pi squared, pi. And these two, we don't know their square root, so we have root LC. Is this clear? Alright. Alright. Do you know that we can collect this guy here and we have 2 pi f, we got to 1 over root LC. Does this make sense? So this is called resonant frequency. This is called resonant angular frequency. This one is angular frequency now, isn't it? So resonant angular frequency. Is that okay? What other thing can we do here? That's all. Sometimes you see in textbook they represented by F naught. Is that okay?
Yeah.
Alright, so that is all on AC circuits. Now let's go to basic electronics. We are typically considering the semiconductors. Have you written these topics? Alright, so we're going to clean. Remind me, we are going to start from particular nature of matter. Let's start from nucleus and just the overlap. Is that okay? So we can just go from here to this, then energy quantization and wave duality. Pause it, please. So the first question says, a transformer is used to operate a 12 volts 24 watt lamp. So it means that the input power P primary, does that make sense? Because you know input is the primary, okay? So input power or inbuilt power of the lamp is 24 watts, okay? That's its capacity. Then so it's used to a transformer. Okay, a transformer is now used to operate this 12 volts. Okay. So it means that it means it's power to the secondary. See, because this is the load. This lamp is the load. Transformer is the what? The source of the transformer is the what? Which is from 240 mains. Is that okay? Let's draw the diagram of that. It's just saying that. So you have I have my transformer like this. So it's drawing from 240 volts mains. Is that okay? And given to, let's do down here, is given to a 12 volts. Is that okay? Now say what is the turns ratio? What turns ratio is required? So we don't know which one is more, which one it is, whether it's a step down or a step up. Of course, in this case, we are going to see is what? Step down. Do you understand now? Is it clear at all? Okay. So the power in this secondary is this. So and the voltage in the secondary is what? 12. So what is the voltage from the source? VP is what? 240. And so what's the primary from the power from the source? We don't know, right? Because we asked, okay, have we asked any of that? No. Calculate the power losses, okay. So we need what turns ratio is required. What turns ratio is required? What turns ratio is required? Okay. So you already know that the turns ratio is NS over NP. Does this make sense? And that turns ratio is equal to the number of turns is directly proportional to the number of the quantity, the voltage, right? So that will be Vs over Vp or Es over Ep. This makes sense, right? So if that's the case, then the turns ratio Ns over Np will be equal to what's Vs? 12 over what's Vp? 240. So 12 here 1, 12 here 2, 0. That will be 1 ratio 20. Is this clear? That's the answer. Now, if the efficiency is 75%, okay, calculate the power losses. Okay. So what's the efficiency? 75%. So we say 75 over 100 is equal to power output over what? Power input, right? What's the power output? 240 now, isn't it? That's the power output. Over what's the power input? X. Power in primary coil is going to be the power input. Is that clear?
Yes, sir.
And power in secondary coil is going to be the power output. So we have 240 over x here. So we now have 75x is equal to 240 over times 100 over 75 over 75. This takes care of this. So what do we have? 5 here and 3. 3 here 25 and 5 here, 3 here 8, 0, 5 here 5, 5 here 16. Does that make sense? So 5 here 1, 5 here 20, 162. 3 x equals what? 320. So that's 320. What's 320? 320 watts. That is the power input. Does this make sense? If 320 is the power input, how much is the loss? Do you understand that question? He said we should calculate power losses. So if it is 75%, in fact, we don't even need to calculate, we didn't even need to calculate this way. We'll just say that, okay, first, let's calculate this and find the power losses. The power losses is going to be, built to discharge 300 and dissipate 320 watts in power, right? But it's dissipating how much? 240, right? So what will be the power losses? That will be 320 minus 240. And what does that give us? 80. So 80 watts is the power loss. Power loss. But the other way we can calculate that is this. Since the efficiency is 75% and it's delivering 240, oh, sorry, 24, not 240, 24 here. 24, so 8 here, so 1.6 here, so 32 here. Is that okay now? Do you see where I made my correction? Okay. So what would this be? 8 watts. Exactly, it's not 240, it's 24. So the efficiency is 75%, and it's delivering 24 watts. If it's delivering 24 watts, so 100% we don't know, right? But it's delivering only 75%. So the amount that is not delivering is the waste, isn't it? So that's what? 25%. So 25% of 25 over 100 of a particular x. No, we are not looking for that x. What we are looking for is that amount that is 25%. Is that okay? So this 75% is 75% of x. Okay, it's the same thing. 75% of x is equal to that 24. It's still the same. Is that okay? It's still the same. So when we get x, we now, do you understand? So that's it. That's it. But like without subtracting here, the other way we can solve it is that 25% is the waste, right? So 25% of 32. How would that give you? 25 over 100 times 32 here, 1 here, 4. 4 here, 1, 4 here, 8. Do you see it? That's what I wanted to do. But I saw you couldn't do it directly. Okay, so that's number 1. Now for number 2. Number 2 says a transformer 550 turns It's also like has, is that okay? The transformer has 550 turns in its primary. So number of turns in primary, N sub P is what? 5,500 turns in its primary. Oh, I wrote it that twice. I wrote that twice. Is used between a 240 volt AC supply and a 120 volt kettle. So what is the voltage in the primary? What's the voltage in the primary? 240. 240 is the mains. AC source is the mains. Mains. That's another word you could hear. Okay, 240 volts. And what's the voltage in the secondary? 120. It now says calculate the number of turns in the secondary. N sub S is what? And recall that the number of turns is directly proportional to the voltage, so it will be equal to V sub S over N sub S over V sub over N sub P will be V sub S over N sub P. Is that okay? You can invert, so you can say NP over NS is equal to NP over NS is equal to VP over VS. So here, what is NS? That's what we are looking for, over NP 5500 is equal to VS 120 over 240. Always make sure that you write your parameters down. Here 1, here 2. So we just use 2 to divide this. So x equal to 5500 over 2. X equals, what did you call it that time? 2750 times. Is it clear? Okay. Who has solved number 3? Alright, let's solve number 3 together. Number 3 says that calculate the instantaneous value of a current if in a circuit it has, so we are calculating the instantaneous current. So that is current at a particular time, right? I sub t or just I. Is that okay? If it has RMS value of this, so IRMS, we are looking for this. IRMS is giving us 15 amps. When its phase angle is 30 degrees, so theta is 30 gram. Now remember that IRMS is equal to I sub naught over root 2, isn't it? Calculate the instantaneous value of a current in a circuit if it has RMS value of 15 amps when its phase angle is 30 gram. Okay? And you know that I is equal to peak value I sub naught sine omega t or sine theta. Thank you. Does that make sense? If this is the case, it therefore means that I sub naught is equal to I over sine theta. Am I wrong? Okay, so if this is the case, it means that we can substitute this guy for this guy. And if we do that, IRMS will equal to instantaneous value over sine theta all divided by root 2. Does this make sense? It therefore means that the instantaneous value I over sine theta is equal to root 2 times IRMS. Does this make sense? Are you still following with me? Okay, so the reason why I'm trying to be explicit, is we could just plug in our values already. But this one I'm trying to be explicit is we can generate another equation. Is that okay? Alright. So I here is going to be what? IRMS root 2 sine theta. Do you get this? So this I naught sine theta is the same as what? IRMS root 2 sine theta. Is it clear? Yes, sir. So I would therefore be equal to, what is IRMS value? 15 amps times root 2 times, that is 1 over 2. Is that okay? Sine 30. So this becomes 15 times root 2 times 1 over 2. That will be 7.5 times root 2. Is this clear? What will 7.5 times root 2 give you? 10.6. Yes, because this one is 1.40 something. So 41 something. So one down should increase it. Okay. Then number 4. Number 4 question says, in an AC circuit, read the question please. Thank you. In an AC circuit, the peak potential difference, so peak voltage is 180 voltage, 180 volts rather. What is the instantaneous PD? What is V sub T or V when it is 1/8 of a cycle? So what is V when it is 1/8 of a cycle? When is 1/8 of a cycle? 1/8 times 360, isn't it? So what do you have here? Here 4 year 90, 4 year 2, 2 year 45. So theta equal to what? 45 granules. I've generated a formula here, right? So you can just use it directly. Because there's no direct connection between them from all our formulas. Oh, there is. Oh, sorry, there is. So V, please not VRMS. I was thinking it was VRMS. Is that okay? It was VRMS too. So instantaneous voltage, if you were giving VRMS, it would be what? VRMS times root 2 sine theta. Exactly. So V here will be equal to what? V naught sine theta. So that will be V equal to V naught, which is 180 times sine 45. So V will be equal to 180 times, what is sine 45? Root 2 over 2. So that will be 90 times this. V equal to what? I hope you remember the sign rules, the common signs. What do they call that? Let me quickly teach you a way to master it, to cram it. Do you know the 5-hand rule? Apart from Tolu, who else knows it? The 5 fingers rule. We'll do it. What is the answer here, please? 127.3 volts. Is that clear? Is that clear? Okay, let me quickly teach you this. So if my fingers are like this, let me make it fatter. Does it look like a hand? 1, 2, 3, 4, 5 is complete now. Which hand would this be? Something like this, right? The right hand facing us. Manage it, please. You know I can draw better, eh? Now I just want it to be fatter. There's a reason why I want it to be fatter. So if your 5 fingers are here, separate them like this into half. Is that okay? That's why I want it to be fatter. And put S here, C here. Sine, cos, sine, cos, sine, cos, sine, cos. Is that clear? Then on all of this, start from 0. 0 granules, 30 granules, 45 granules, 60 granules, 90 granules. It works for only these 4 or these 5. Is that okay? Now the rule is this. Square root of the amount of fingers over 2. That's the rule. So for example, if I want to take sine 0, sine is on this side, right? How many fingers do I have left on this side? Nothing, right? So it will be the square root of 0 over 2. Square root of 0, 0, 0 over 2, 0. So sine 0 is equal to what? 0. Does that make sense? How about cos 0? For cos 0. Cos is on this side, right? Do you see where I first separated it? How many fingers are on this side? 4. So it will be the square root of 4 over 2. What is square root of 4? 2 over 2. What would that be? 1. So what do we have? Cos 0 is what? 1. Are we clear? The next one, sine 30. Sine is on this side. How many fingers do we have on this side? 1. So we say square root of 1 over 2. Square root of 1 over 2. Does that make sense? Cos 30. Cos is on this side. How many fingers have we here? So that will be root 3 over 2. What will this give us? Root 3 over 2. Does that make sense? Which is 0.8660. How about for 45? Sine 45 granite. Sine is on this side. Square root of 2 over 2. That becomes what? Root 2 over 2. How about cos 45? Root 2 over 2. Is it clear? Then how about sine 60? On this side, root 3 over 2. How about cos 60? 1 over 2. If you don't understand, raise your hand. Did you get the trick?
Yeah.
Alright. It works for only sine and cos. And that's what you need in your jam. Those are the ones you need in jam. Practice it when you get home. Is that okay? Alright, let's solve the last question then. It says a source of EMF 240 volts and frequency. So let's write it that way. So source of EMF 240 volts. It means that what? V what? Is that VP or VS? A source of EMF 240 volts. Is that VP or VS? That will be VP because it is from the source. It's connected to the mains. It's equal to 240 volts. And frequency. Frequency is what? 50 hertz. It's connected to a resistor, an inductor, and a capacitor in series. So what kind of circuit is that? RLC. Okay, so your formulas for RLC should begin to come to your mind. When the current in the capacitor is 10 amp, so current in capacitor is 10 amp. So current in capacitor is 10 amps. The PD across the resistor is voltage across resistor is 140 volts, and that across inductor, voltage across inductor is 50 volts. Draw the vector diagram of the PD across the capacitor and the resistor, the inductor, the capacitor, and the resistor. So the vector diagram is very simple. So you know that since it's RLC circuit, I showed you already, right? Voltage and current, how would they be? Voltage and current they'll be in phase. Voltage and current will what? So we have this diagram that voltage and current are in phase. In a capacitive circuit, what will happen? Capacitive, who will lag, who will lead? So this is V sub C and this is I sub C. Is this clear? This is capacitive. Inductive, who will lead? Voltage will lead. Do we understand? By the time we combine these three, what do we have? We have a shape like this. Who will be up? V sub L. Who will be here? V sub R. Now, considering all the, you could use V sub L here, V sub R and I. Do you understand now? Do you get it? Alright, because if you say V sub R and I here, it means that in this case, relative to this and this, current is lagging behind voltage, V sub C. Relative to this and this, I is what? Leading voltage. Is this clear at all? And why are you looking like we've not done this thing before? Voltage will lag here because it's what? In a capacitor, right? So this is the vector diagram basically. Okay, the vector diagram should now show all the directions. So by the time again you combine this, you're gonna have the voltage. So this one is in parallel, is in vertical position, right? Vertical axis. This one is in horizontal axis, right? Where will the resultant go? The resultant will be like this. Is that okay? All right. So, and that will be V. The resultant V will be like this. Is this clear? But the formula that combines them here is going to be V equal to what? V of V squared is going to be what? Square root of V sub R squared. What we did now, those things. Plus what? No, voltage now. V sub L minus V sub C squared. Just the same way as, okay, was only resistance we did that time. This is another formula. This is the same idea that in an RLC circuit, if it was RL circuit, it will be V squared equal to square root of V sub R squared L circuit plus V sub L squared. You understand? The idea has not changed. If it was LC, okay, LC now will be just V equals what? V sub L minus V sub C. Is that okay? The same way as we said that X will be equal to X sub L minus X sub C without putting square root or anything. Is that okay? Yes. Do you remember why? Because they are in the same axis. It's not vector that we're adding. Do you remember? These vectors are in the same axis. Look at it. Up and down. So if you are asked the voltage in VC and VL, what will be the phase difference between them? VC and V sub L. Yeah, they are out of phase by how many degrees? 180 degrees. Is that clear? It now says calculate the voltage. Oh, we'll need that. Calculate voltage across the capacitor. So V, so since it's RLC circuit, since the circuit is RLC, now remember that voltage across the capacitor will be equal to, let's first get the formula. V equal to what? V squared, square root of V squared plus V sub R squared plus V sub L minus V sub C all squared. Does this make sense? So we're looking for this. We'll make this, okay, let's not make this subject. Let's just plug in our values and see what we can do. You get what I'm saying? I do not complicate matters. So what is our voltage? The voltage from the source itself is what? 240. So we have 240 is equal to the square root. Okay, let's return square root here so that it becomes squared here, isn't it? Equal to V sub R squared. What is V sub R? 140 all squared plus V sub L 50 squared minus V sub C all squared. No. These together, right? 50 minus V sub C all squared, isn't it? So here, 240 squared will give us what? 24 times 24. 240 times 240 is equal to 14 times 14, 196. Plus, we now have 50 minus, is it 196 or 198? 50 minus, yes. 50 minus V sub C all squared. This guy goes here. So we have 50 minus V sub C all squared is equal to 57,600 minus 19,600. Are you here? 0, 0, 0, 38, no, 28. Okay, yes, this one is okay, 38, yes, 38. So 50 minus v sub c all square is equal to 38,000. Take square root of both sides. So we have 50 minus v sub c equal to square root of this 194.94. Are we clear? So v sub c will now be equal to, by the time we, it become minus, right? Okay, let's calculate first. V sub c will be what? 50 minus 194.94. What does v sub c give us? Minus what? 144.94. Okay, volts. I'm thinking this VC will be like VC, since VC is down, that'll be negative direction. Do you understand? So it's qualitative there, right? So B now, capacitance of the capacitor. What is capacitance? But this capacitive reactance. Is that okay? It's C we are looking for. And what is the capacitive reactance first? Is that okay? What is the capacitive reactance? So how do we get capacitive reactance? Capacitive reactance is equal to 1 over 2 pi Fc. Okay? What's the frequency? Are we giving anything about frequency and all those things? Okay, 50 hertz. But I'm not giving C. And neither are we giving X sub C. Right? Yes? Okay, yes. Since we have gotten V sub C, voltage across the capacitor will be equal to what? Current times X sub C. Do you remember this? Do you remember? So we have that V sub C will now be that guy, 144.94 is equal to current. What's current? 10 amps, 10 times X sub C. So that C, X sub C, you see we are not using the negative. Is that okay? Because it's qualitative. X of C what? 14.5. 14.49. Is that okay? Alright. So this is X of C. Then recall that X of C is this. So we'll now say that by the time you work the math, C will be equal to 1 over 2 pi Fx of C. Am I wrong? No, just interchange it. Leave this one here, put this one here, put this guy here. Is that okay? Right. So C will be equal to 1 over 2 times pi times 50 times 14.5. Pi is 3.142, but we're not giving, so let's leave pi. Let's include pi now. For most questions, you'll be giving pi, or you are not giving pi. Pi will appear in your option. So let's leave pi. So C will be equal to 2 times 50, 100. 100 times this 1, 2. 1400, 14500, right? 1, 2. 1450 pi. Are we clear? Farad, right? Oh, 1 over this, yeah? Okay, thank you. So see, we got 1 over 1450 pi. Do that. Multiply 1450 times pi. That's times 3.142. Then use it to divide 1. See, we got what? 0.00001. 2.19, 2.2 times 10 to the power minus 4 farad, right? Are we good? Remember that the opposition that the capacitor offers and the one that an inductor offers, they are very negligible, they are small. Do you get it? They are very small. All right. Then the last one, the inductance of the inductor. Okay, let's see what that will be. What will be the inductance of the inductor? Since we have V sub L here, right? We have V sub L. V sub L will be equal to I times X sub L. Remember that, right? So V sub L is already given to be 50 equal to what is I? 10 times X sub L. So what do we have? You see that inductance will be, the other guy, inductance will be greater. That's why we always subtract capacitance from it. Do you remember? So this takes care of this. X sub L equals what? 5. And recall that X sub L is equal to what? 2 pi FL. Do you remember now? So 5 will be equal to 2 pi times F. 50, right? 50 times L. So here 1, here 10. 20, 1 over 20 pi is equal to L. Are we good? So divide. L will be equal to what? Just say 1 over 20 times 3.142. 0.16. What's the unit of inductance? Henry. Are we good? Alright, so that's all about that. Is it hard? Okay, so let's go to the next topic. Now, what is a semiconductor? No, first, materials based on their conductivity in the world are classified into how many? Based on their conductivity into 3, right? Which are what? Conductors, non-conductors or insulators, and what? Semiconductors. Conductors are the ones that allow electricity to pass through them, while non-conductors or insulators are the ones that do not allow electricity to pass through them. The insulator that is used in a capacitor is called what? It's also called what? The insulator that is used inside the capacitor, the insulator that is used in between these plates, what do we call it? Dielectric. Do you remember? You do not remember. You are saying yes or no. There's only one person that said this and you're saying yes. Okay. I didn't hear you. When you're talking, you talk loud. You shout. Do you understand? It cannot affect whatever I'm shooting here. You know what I'm saying? Dielectric. Because you're not sure, if you are confident enough. Dielectric, sir!
Yes, sir.
So we have conductors, we have insulators, we have what? Semiconductors. Now listen up. Now why are conductors conductors? Because they conduct electricity. And remember that there's a relation between, so the ability of a substance to conduct electricity is known as what? Conductivity. But its ability to not conduct electricity will be called what? Resistivity. Is that okay? And we said that resistivity is the inverse of what? Conductivity. So it means that conductors have what? High conductivity. But non-conductors have what? High resistivity. Does that make sense? Conductors have high conductivity, low resistivity. Conductors have high conductivity, low resistivity. While non-conductors have what? High resistivity, low conductivity. Do you understand? All right. Now, semiconductors are the ones that can act as both a conductor. They are midway between those extremes. Is that okay? So they can act as a conductor if a proper amount of energy is given them. Is that okay? And they can act as an insulator or a non-conductor if no energy is provided for them. Is that okay? So what makes a conductor conductor? A conductor is able to conduct electricity because its nucleus. So if we were to draw the energy, what do you call that? This thing, energy level that exists in the nucleus. In the, if you were to draw an atom, good, an atom of a conductor. So what we have is this: we have our nucleus, right? The core surrounded by energy levels, isn't it? Now, if you fill in electrons, I'm not filling everything now. Is that okay? So what is the valence electrons that this guy have? 2, isn't it? Now, you see, this last energy level here is called the valence electron shell. It's called what?
Valence electron shell.
So in the valence shell of a conductor, the electrons that are there are free to move. Is that okay? And so that's why a conductor is able to conduct electricity. What do you mean by they are free to move? Now, beyond this energy level, there is another energy level that is known as the conduction band. It's known as what?
Conduction band.
So this thick one I'm drawing here is known as the conduction band. Now, if you look at the valence shell, this valence shell and the conduction band, what's the distance? Is there any much distance between them? Okay, for you to see it clearly, look at that of a non-conductor rather. These are our what was that? Levels. Are you with me? So for this particular non-conductor, for this particular non-conductor, there is an energy band around it. So look at the valence shell and look at the conduction band. What's the difference between the valence shell of this and the conduction band for a non-conductor and the valence shell and the conduction band for a conductor? What's the difference? The distance, right? The distance is higher in what? In non-conductor. Is that okay? So for a conductor, once you don't need much energy to pass into them before electrons begin to what? To move out. Why? Because the electrons, the conduction band and the valence shell, they overlap each other. They are so close that in some cases, such as we find in copper, they do what? They overlap. So because they overlap, electrons are free to what? Move. Electron does not need much energy to what? Escape the conduction band. Are we clear? But for this guy, there are other energy levels here that this guy cannot reach. There are the electrons in these valence shells. Electron in the last shell, which is the valence shell, cannot reach. So it needs some amount of energy for it to be able to what? Move beyond it. Is that okay? And in fact, high amount of energy. So because that amount of energy cannot be provided for it, we say that a non-conductor, the nucleus has a high pull or high hold or high, is holding on to the electrons tightly. Do we understand?
Yes, sir.
Because the electrons cannot move out of the valence shell beyond the conduction band. But for a semiconductor, we have our nucleus here, like this. The conduction band is just somewhere around here. Do you notice that the conduction band and the valence shell are very what? Close. So because of that, if you provide an amount of energy for them, they are able to do what? Move out of the conduction band. Does that make sense? Okay. So now let's talk about semiconductors. Now there are two types of semiconductors. We have the intrinsic and what? Extrinsic. What is an intrinsic semiconductor? We have the intrinsic and the extrinsic. What's an intrinsic? It's one that cannot conduct electricity. Why? Because it has not been doped. Because it has not been what?
Doped.
But extrinsic has been doped to something, so it's able to what? Conduct electricity. Do you understand? So how do we dope them? Now, semiconductors on the periodic table are primarily silicon. We didn't even mention metals that are conductors. Go on, copper, aluminum, most of our metals, right? Okay, how about non-conductors? Carbon, it depends. Carbon can conduct electricity in its what? Amorphous form, right? That's what? Is graphite amorphous? No. In its the second crystalline form. Graphite is also crystalline now. It's the second crystalline form, right? So graphite can conduct electricity, but it's weak crystalline form. Diamond cannot conduct electricity, and that's the major difference between graphite and diamond. Remember we said that, but if you heat graphite to a very high temperature, you can make diamond, right? You can make diamond, artificial diamond, from heating graphite. Is that okay? But the point is this, that graphite can conduct electricity. In fact, can wood conduct electricity? Can stick conduct electricity? But if you burn wood to become charcoal, charcoal can do what? Do you understand now? So it means you have to, yes, it means you have to, by burning it to become charcoal, what has happened? You have increased the energy. Do you understand now? So by imputing some amount of energy into a particular system, it might move from being a non-conductor to being a what? A conductor. Is that okay? All right. Bless you. So then we now have semiconductors. But non-conductors, they are basically plastics, gases. Do you understand? All gases, none of them can conduct electricity. Is that okay? Oxygen, nitrogen, or any gas, they can't conduct electricity. The only form in which they can conduct electricity is what? When they go to what? Plasma state. Do you remember? And that's what differentiates gases from plasma. Is that okay? All right. So my point now is this. Examples of semiconductors, we have silicon, all those guys on that scale there. Silicon, germanium, arsenic, gallium. All right. So silicon is Si. This guy is what? Ge. This guy is what? Yes, here is argon. Gallium is disobey, right? Okay, so all these guys are semiconductors. Now, this is the way the structure of a semiconductor is. Now, a semiconductor has 4 valence electrons. Is that okay? So, in its lattice structure, it has 4 other atoms attached to it. An example is in silicon. It has 4 other silicon atoms attached to it. Each silicon has how many silicon attached to it? 4 silicons. Why? Because silicon is what number? It's taking you 1 year to remember silicon.
14.
Okay, 14. So by the time we fill 2 in the first shell, 8 in the second shell, what do we have remaining? 4, right? So we have the 4, we fill them here. That is 1, 2, 3, 4. Are you with me? So around this nucleus, around this silicon, you find another silicon. Are you with me now? Let me compress it. Another silicon that will be covalently bonded to that silicon because they will share their electrons. That's covalent bond, right? So this guy also has an 4 around it, isn't it? So to bring one of its 4 to bond to this, to bring one of its 4 to bond with another guy that has 1 too to bond with it. You see the way we are connecting them now? This guy to bring one of its 4 to bond with this guy. This guy will use one of this one to bond with one of this guy. This guy too has, do you understand? Like this, and that's the way they are forming structures like that. This one too, one of his bond, one of his bond, one of his bond. This one is from this guy, this one from this guy. You get what I'm saying now? And like that, like that, like that, you're going to see 4 guys around each silicon. Where are we going to get to, right? Good. So now in some cases, you know, that was the question that guy said asked me. He said if it's covalent bonds that holds the diamond structure completely throughout, that what does it mean it never ends? So and I said, I think I told you what I said. I said because of naturally occurring diamond, the process is not perfect. Is that okay? Impurities tend to come in. So with the presence of impurity, there is what? Intermolecular bond. Covalent bond is a what? Is an intramolecular bond, right? So it's an intramolecular force. So since it's an intramolecular, the bond is strong, very strong. Is that okay? But because of the natural process of forming compound or forming diamond, for example, now can be impaired by the presence of impurities and all. What will happen is that those impurities will bring about intermolecular. I told you intra means same, between the same molecules. Is that okay? Inter means between different molecules. Is that okay? And that's the same case here. So in the extremes, the extremes will be formed by the presence of impurities in these compounds. Is that okay? And those ends are the possible conductive ends if energy is provided for this system. Is that okay? All right. So, but the point is this. This is what we have here. I want this thing to be a continuous conductor. Is that okay? A permanent conductor. How do we make it into a permanent conductor? We take it through the process known as doping. It undergoes the process known as what?
Doping.
So what do we do in doping? We basically add what we call an impurity. Is that okay? There are 2 types of impurity that we can add. Is either a positive impurity or a negative impurity. Now, positive impurities will be impurities that create a hole. Will be impurities that do what?
Create a hole.
And negative impurities are the ones that create the presence of valence electrons. Are we there? Okay. So doping means adding impurities to this guy. And when we mean impurities, we don't mean dirt. We mean another atom to this. Is that okay? So all of these guys here are silicon, 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 silicon. Okay. Now looking at this particular silicon, if you wanted to dope this silicon, you know what you would do? Rather than add this guy, this second silicon here, this is what we'll do, or here's what we'll do. We'll add, if you want to dope this entire structure rather, we'll add to some portions, different portions here, we'll add something like phosphorus, for example. Let me draw the first 20 elements so that you understand what I'm trying to do. You know, don't think I'm inventing it. It's not anything, it's nothing hard. We have the first 20 elements like this. Even the first day I taught you, I still drew it, right? So you learn it, you don't cram it. So hydrogen is what? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Okay, so now silicon is on this side, right? Are you with me? Okay, now if I want to dope this guy, I can dope with either phosphorus, nitrogen, or the guys under it, or dope with aluminum, boron. Is that okay? If I dope with aluminum or boron, what is the valence electron that are here? Group 1, group 2, group 3. What's the valence electron here? How many valence electrons do they have? 3. How many valence electrons does this one have? 5. Is that okay? That's why they are group 5. Group 4, group 6, group 7, and group O or group 8. Are you with me? So the valence electron here is 3, the valence electron here is 5. So this lattice structure require how many bonds? 4, 4 require an atom that has 4 bonds around it, right? Okay, so meaning that if I dope with carbon, I'll still be wrong because it will still not conduct electricity. Is that okay? So if I want to dope now, I will dope with aluminum or boron. If I dope with aluminum or boron, what will exist? Is it more electrons or a hole where there's no electron? A hole, right? So let's try what we are trying to, let's show it. For example, let's dope with aluminum. Aluminum is number 13, right? So the octet structure will look like this. We have 2 will fill here, right? 8 will fill here. How many remain? 3, right? So 1, 2, 3, right? So let's dope with this guy. Let's say we add aluminum here. If we added aluminum here instead of the silicon that was there, so what will happen is that this guy will get, this side will get 1, right? This side will get 1, so this structure will not be affected. This one here, 2 here will get 1. Then the second one will be from silicon. Are we there? So this structure here is still perfect, right? You understand what I'm doing, right? If you don't understand, raise your hand. This is how many electrons must be around this thing? I just said octet structure, 8 electrons, isn't it? So those 8 electrons must be what you have around each guy. So but this guy, the silicon, has only 4 valence electrons. When you do the, okay, maybe because I didn't show you, this silicon now, 1, 2, the silicon is number 14, right? Do you know that? Okay, silicon is number 14. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now let's split it 1, 1. 11, 12, 13, 14. So is this complete? No, because it needs what? 4 more. It has to be 8 on the outside shell. Do you understand? So what will it do to get that 8? It will now bond with another guy that can supply it 4. So that's what we have. If I show you a silicon lattice like this, if I show you a silicon lattice, so everything there is comprised of silicon atoms, and this is the way they are bonded on the atomic scale. Do you get it? Okay, so this guy will now bond with another silicon on this side. That silicon too, we have this kind of structure, right? So we have 4 on the outermost, right? So on one of the sides we have 1. So for this one, this side is already complete 2. To bond with another silicon here, that silicon will provide it 1. To bond another silicon here, provide this 1. Bond another one here, provide this 1. How many do you have here now? 8 complete for this guy. This guy too, for it to be complete, to bond with another one. Do you now understand? So that's what we did here. So to dope is to remove one of this guy and put a guy that will provide, that will destabilize the structure kind of electrically. Do you understand? So in this case, if we dope with aluminum has 3 to give. So if he gives this one 1, this guy complete 8. Give this one 1, this guy complete 8. Now, if you give this one 1 2, okay, so give this one 1, complete 8. But on this side, there is no electron here, right? So for this guy will not get 1. Only silicon will be contributing. So what do we create here? A hole for electron. Do you understand? Now, yes?
If we look for that, maybe we look that pipe, we do nitrogen.
We dope with nitrogen.
Yes.
And that's what we want to do now. We have doped with aluminum. Let's dope with nitrogen. So we dope with nitrogen, for example. We dope this thing, this structure, or this silicon lattice with nitrogen. That's the term. So let's dope it with okay. I just do nonsense, right? Okay. So now watch this. So this is my silicon. Everybody was happy. Everybody was happy here initially. Everybody got what they wanted. Are you with me? So now I decided to destabilize the structure electrically. I will remove one of the silicons and dope with. Now it's only one. Oh, I'll dope in different sites. Is that okay? I'll dope at different portions. So just leave it. Now I'll dope at different portions. Now in the second portion, the second silicon lattice, I will dope now with either nitrogen or phosphorus. Let's dope with phosphorus. Is that okay? If we dope with phosphorus is number 15, isn't it? So for number 15, this will be the way the octet structure is. Inside we have 2, 8, 5 outside, right? So we have 1, 2, 3, 4, 5. Is this clear? Okay, so we dope with this guy, then this is what we have. So this is now phosphorus. All of these are silicon, silicon. So we will now remove one silicon and put phosphorus here. So by putting phosphorus here, this is what will happen. Phosphorus will have provided everybody with 111, right? But we still have an extra one. So that extra one will now come here. That extra one will now be an electron. Is that okay? So because of that, electron is now free. And can electron exist alone? Electron has high energy, right? So it will now flow. It will now begin to flow. So this guy, this silicon will now become conductive. Is that okay? This one is also conductive because it permits for electron to what? Enter. So for you to now complete the system, what do? You now bring this guy and this guy together. So electron will flow from where to where? From here to here. Do you understand? So this guy here is called the n-type doping. Is that okay?
Yes, sir.
The n-type because it's negative, because the electron that is giving out electron. Do you now remember?
Yes,
so this one is called what? P-type doping. P-type positive, n-type negative. Is that okay? So what are the major what are the major charge carriers in an n-type doping? What are the major charge carriers? The major charge carriers in an n-type doping is electron. What are the major charge carrier in a p-type doping? Old people. Then what are the minor charge carrier in this? Holes. Why? Because the position that this electron leaves to will be filled with something else. Will create a hole here, but that is unstable. Do you understand now?
Yes, sir.
So holes are minor charge carriers in n-type. Electrons are what? Here, electrons will be minor charge carriers. Do we understand?
Yes, sir.
Okay. Should I put that down in writing? I said here, major charge carriers. Major charge carriers. Electrons. Major charge carriers. Holes. Is that clear?
Yes, sir.
So now, the moment we bring this together, we form what is called a diode. We form what is called what?
A diode.
So doping is adding impurity to what? To a semiconductor. Yes. And that impurity will destabilize the electrical property, or we change the electrical property of the guy. So we said that a diode is made when we what? Combine the n-type and the p-type semiconductors. Is that okay?
Yes, sir.
We make a diode when we had that. And the diagram, the electrical symbol for diode is this. Do we understand?
Yes, sir.
Which portion is positive, which portion is negative? This part is what? This side is what? Listen, this is an arrow, see. The direction of arrow is showing the direction of conventional current. Where's the direction of conventional current? What's the direction of conventional current? Do we understand now?
Yes, sir.
So, or you say where the bomb is facing.
Yes.
Do you understand?
Yes.
Where the buttocks is facing. The buttocks of this thing. That's how to remember it. You do like this. Or you do like this. And it's to show them the shape like that. Inside your hand, you remember the man did like this. So his bonbon is facing that side, so that will be negative. His face is positive. Do you understand now? You are facing positive. You are open to positive. Are you with me?
Yes, sir.
And there are different types of diode. We mentioned the Zener diode, the signal diode. What did I call Zener diode for you? The breakdown The what? Diode. The signal diode, the power diode. There are about 4. We have the signal diode, power diode, Zener diode, LED, God bless you. Light emitting diode. LED is what? Light emitting. Which one do we use in our radios and those common guys? Is the signal diode. The one that we use in our radios, our common appliances, small appliances. Is the what? Signal. Is the what? Signal diode. Is that okay? Now, you see, this LED, LED emitting diode, this is the own symbol. The symbol of Zener diode is like this. You see something like this. This is Zener diode. It's also a diode. Is that okay? Alright. But don't worry, just leave this one. But my point is this now. Now, one of the functions of a diode is that it helps. Okay, first, let me show you how the condition is. So we have a portion here. So we have the P type here and we have the N type here. So the P type, listen to this condition. There are two connection when you connect a diode to a DC circuit. When you connect a diode to a power source, basically, you create what is called a bias. You create what is called what?
A bias.
And there are two types of bias. We have the what? Forward bias and the backward
bias.
Okay. So in the forward bias, in what direction does diode allow electrons to flow? Is it forward bias or backward bias? The forward bias. So electron current only flows through the diode in what? In the forward bias. Current flows in the diode only in the what?
Forward bias.
It's funny now. Current only flows in the diode in the what?
Forward bias.
If you connect in the reverse direction, we have the reverse bias or reverse bias. Is that okay? Forward bias or reverse bias. If you connect it in the wrong way, so the forward bias is this: when you connect the P junction to the positive plate, is that okay? And you connect the N type to the what? Negative plate of the our voltage source, our electrical, our cell or battery. Is that okay?
Yes, sir.
But if you interchange it so that you now connect the N type to the positive and you connect the P type to the negative, current will not flow. Let me explain how current flows in this first connection. In this first connection, there are two layers here, the P type and the N type. Then there is a third layer in between. We call it what? The depletion layer or zone or region. Is that okay? Now the depletion layer, when you connect it correctly, the depletion layer, what happens to it? It constricts. Do you remember? It shrinks, constricts or shrinks. Why will it shrink? Because current is flowing in this direction. The electrons are moving in this direction, isn't it?
Yes.
So you are permitting the actual movement of electrons. So electrons are already moving from negative to what? To positive. So because of that, you are shrinking the holes, the space between them. Is that okay?
Yes, sir.
All right. But if you connect wrongly, such that you connect the negative to the positive here, and connect the positive to the negative here, this is what will happen. Electrons are moving in this direction here, right? But current is flowing in this direction, isn't it? So it means that electrons are drawn in this direction. Does that make sense?
Yes, sir.
Does it make sense to say that? Electrons are coming from here, isn't it?
Yes, sir.
If electrons are drawn in this direction, because it's positive, it will be attracted to electrons, isn't it?
Yes, sir.
So it means that it will widen the gap and electrons will move away from here. Electrons that are supposed to be moving like this this guy wants to draw electron. Actually, if electrons are moving like this, it means positive charges are moving like this, isn't it? And this is the positive part, right? So positive charges will be moving, drawn towards this place. What will happen to the depletion zone? It widens. Depletion zone does what?
Widens.
So because of that, we create what? A backward or reverse bias, and current cannot flow. Is it clear?
Yes, sir.
It is clear to you, and you are sure. Come, and you can come and explain. Raise your hand. You can explain. I will give you marker. You to know you can explain. All right. Okay. So now the last thing we'll talk about is rectification and transistors. Now rectification is the process by which so basically what we are saying is that since if you connect it wrongly, if you connect this thing wrongly, that is if you flip it over, you connect it wrongly, current will not flow, right? So it means that a diode is another material that allows current to flow in what? In one direction. Is that okay now? It permits only unidirectional flow. So it means that you can use a diode to convert AC to what? Does that make sense?
Yes, sir.
Before we have seen in generators that you can use what to convert AC to DC. What did we say you can use in AC generators or AC motor? What do you use to convert AC generator to DC generator? You remove the what used to be in an AC generator. What does it use? Is it split or slip rings? So AC uses slip rings. AC generator uses slip ring. When you change that slip ring to split ring, it will change it to what? DC. It will change it to what?
DC.
You're not reading notes, right? Hey. When is jam? Or when is UME, right? That's the exam. Okay. When is UTME or UME for short? UME is in 3 days, Abby. And you are not here reading. So it's the day before your jam, you now read. I God save you in Jesus. And I know some of you are watching too that, like some of my students here. Some of my students here said they don't read notes. I pity you. I hope my face show well. I pity you. See, let me tell you, it's not a coincidence that they call it jam. It's not a coincidence. They did not call it jam. It's not because the body. Why did the body not say UTME body? Have you ever thought of it like that? Could they not have said, is there another name for WAEC? Okay, SSE, wow, SSE, and that's the body, right? Okay. But at the end of the day, why did they not? You see the improviso in that one? WAEC. It turned this exam, yeah? Then the body was said or whatever. Is it SWS? Now listen. Did you not see that there's a combination of WAEC? Eh? Look at UTME. Eh? They changed to what? To jam. You think it's a coincidence? Eh? What they mean is it can jam people. It can do what? May it not jam you in Jesus' name.
Amen.
May it not jam you too. But I pity you if you are not reading. Did I just say I pity you? I did not pity you. And be laughing. You see? Yeah, I'm talking to you too. Don't worry. All these things that we have covered more than 1 million and one times. Anyways, what did I say? Let's come back to class. No, don't click off yet. Let's come back to class. Everybody knows the BT, you understand? Let's come back to class. You know, today I'm just thinking about it. Why do they call it jam? No. not youth med, not youth meb, the UTME examination board. Joint admissions, it's just English, is John. Is what? Yeah. God forbid for you in Jesus' name. Where were we, please? Rectification. What is rectification? But if you are reading though, I celebrate it. So I do not say I did not celebrate it. If you are reading though, I celebrate with you. Because you have passed, see that you read self. Jam, when your questions will come to you as one that has read. Your questions will come smiling. You understand? What is rectification? Rectification is what? The process by which what we use a diode to convert what? AC to DC. Is that clear? And there are two types of rectification. What are they? Halfway rectification and what? And full bridge. Yeah, it's also a bridge, don't you know? It's also a bridge now. Do you understand? So in halfway we use only one diode. Is that okay? But there is inconsistencies with it. Is that okay? That's some problems. So we use what? The full one is the best. Is that okay? The full wave is the what? Is the best. Okay. So then there's another thing called the transistor. Is that okay? Now the transistor is comprising of it's comprised of semiconductors too. Is that okay? So, but in this case, a transistor works like a diode too. Is that okay? Because a transistor can also convert AC to, it can also work as both a conductor and a non-conductor. Is that okay? All right. That's all on basic electronics. Is there any calculation we did on this part? There was no calculation we did, right? All right, let's go to the next topic. Are you happy with me? What's the next topic, please? Water. Quanta, right? Okay, let's begin quanta then. Okay, let's begin quantas. All right. So now, how do we even go now? How do we go? I'm just going to treat everything like in a. Before we go to photoelectric, no, let's go to photoelectric effect. Let's start from photoelectric effect. Is that okay? What does photoelectric effect? The process of generation of what? Photoelectricity. What's photoelectricity? Electricity generated from what?
Photons.
Photons of sunlight, right? Of light, okay. Of light, basically. So now, this is what happens. It was observed by this guy, Frank Hertz. No. Was it Frank Hertz? Yeah. It was just Hertz that carried out the experiment. Is that okay? It's just Hertz. Hertz that carried out the experiment. Gustav Hertz. I carried out the experiment in 1887, yeah? And in that experiment, he saw that a polished metal plate can actually do what? Emit electrons. Is that okay? Or cause electrons to flow or eject electrons. Either way you bring talk about this. Just what I'm saying. So, and now why is this phenomenon very, very important? It's important because there was something about the emission of that electricity, of the emission of that electron, of those electrons. Now, is the fact that it was, in fact, this scenario brought about a different field called quantum physics. Is that okay? In classical physics, we learned that waves, the intensity of a wave affected the frequency of a wave kind of affected the intensity and all of those things. Are you with me? So No, intensity of wave. What is intensity of wave? What did it affect basically? The amplitude, right? Do you remember? The intensity of wave affects what? The amplitude. Is that okay? All right. But we also learned that um, by the idea we get from classical mechanics, we when a photon of light, when light is incident on a metal plate, a high frequency light, are you with me? A high frequency light, if it's incident on a metal plate, what should happen is that electrons, a lot of electrons should be emitted. Is that okay? But when they did the study, they discovered that the amount of electrons that were emitted were not equal to the amount of frequency of light that was shown on the metal plate. So that is, the emission of electrons did not depend on what? On the what? Frequency. Are you with me? Are you with me?
Yes, sir.
Or the frequency of the light that was emitted, did not depend on the energy of the electrons. Is that okay? Or the energy of the electrons did not depend on the frequency of light that was incident on it. I'm just interchanging them. Are you with me? They discovered that as they increased the intensity of the frequency of the light, it did not make the electrons to gain high energy to move out. Are you with me? So they now discovered that there is a particular frequency of light that must be incident on. So I said I will rewind because the mic switched off. So photoelectric effect was studied by Gustav Hertz in 1887, and what he discovered was that, or he found out that when a polished metal plate, and notice I'm mentioning the word polished because the orientation of the metal plate or the nature of the metal plate to determine whether there will be emission of electrons. Is that okay? Or the smoothness of the surface, right? So notice that in most of your solar panels, what do you usually see on top? Flat, glassy, smooth surface, right? Yes, because of the it's because of the emission. Okay, so we said that why was this why was it very, why was it intuitive? It was because in classical physics or classical mechanics, we said that the energy that a system has, or the energy that wave carries, are you with me, was dependent on the energy, yes, the energy that wave carried was dependent on the frequency of the wave, such that the higher the frequency of the wave, the higher the energy it carried. Does that make sense? Okay. So, but it was discovered by Albert Einstein actually used the word quanta. Is that okay? Which meant photons of light. Now I'm going to explain what this meant basically. But it was this phenomenon, this idea that brought us to the field of quantum physics. Is that okay? And that was because we began to see that the frequency of the light did not determine the amount of energy that the electrons needed to escape the metal plate, right? Polished metal plates will eject electron, emit electron when irradiated, right? Yes. So, but it was discovered that the frequency of light that was incident on them or that was used to irradiate them did not determine how much energy the electrons will gather, will get or gain to escape the metal plate, isn't it? Okay, but they discovered that, or what they discovered was that there was a particular frequency known as threshold frequency. Threshold. This way should be spelled, right? Am I correct or wrong or correct? what they discovered was that there was a particular frequency known as the threshold frequency, or F sub naught, at which the electrons actually gained a particular amount of energy, or the minimum energy needed to escape that metal plate. Is that okay?
Yes, sir.
So the frequency, the increase in the frequency did not translate to the increase in the energy that the electrons gained, isn't it? Because this whole thing is about vibration. Do you remember when we did transmission of light? We said those atoms will receive the electrons, the wave, the frequency of light, and vibrate at the same frequency. Is that okay? So if they vibrate at the same frequency, what they do, they'll pass on that energy to the neighboring distance and do what? Transmit it. But those are what? Transparent objects. But some opaque objects, when they receive that amount of energy, they will do what? They don't vibrate at the same frequency. So because of that, they will return that frequency of light. Is that okay? They reflect it. We call it reflection. Are you with me now?
Yes, sir.
Okay. So now, so this amount of frequency, which is the threshold frequency, was the frequency, the exact frequency that a particular electron of a particular electron needed to escape the surface of the metal plate. Are you with me? Yes, so it was now discovered that the energy was actually dependent on the threshold frequency, not just the amount of frequency. Is that okay? Yes. Not just the frequency. So E is equal to HF naught. Now this E is the minimum energy required to escape that metal plate, and we call it work function. We call it what?
Work function.
Work function is the minimum energy. So if the metal plate was at a particular level like this, the electrons are locked in here. For example, electrons are locked in here. So the minimum energy amount of energy required to first move out of this plate, to escape this plate. Just like we did in this thing. We said that electrons can actually move from one energy level to another energy level. And we said if electron move from one energy level to the other, that is higher than it, what will it do? Has it gained energy or lost energy? It has gained energy. If it moves from what? Low energy level to high energy level. But if it moves from low energy level to lower energy level, is what? To lose energy. All right. So this case, the energy that is needed to go from here to here, if we plot a graph of that guy, there's a work function will be here, negative phi. Is that okay? So phi is used to represent work function. Is that okay? Phi is giving us HF sub naught. Is that okay? Yes, so if we plotted the graph, we'll see that there's a minimum amount of energy that is needed to escape this band. Then there will now be some more energy. If the energy that is supplied to this electron, to that electron, is enough, then it will now have some more energy to move out. Do we understand?
Yes, sir.
Is it clear?
Yes, sir.
All right. So H here is Planck's constant, right? And who was Planck? The guy that worked on what? Black bodies, right?
Yes, sir.
Black body emissions. Planck's constant. And what's the value? 6.63 34. All right. Joules seconds. Because frequency is per seconds. You remember? Since frequency is equal to 1 over period, that will be per seconds. So Planck's constant will be E over F naught. So the energy is joules times seconds. This one is per seconds. The rest goes up. Does that make sense?
Yes, sir.
Okay, now look at this. So let me go back again. So I said that I cleaned that. So work function is the minimum amount of energy needed to escape that conduction band. So the remaining energy supplied here to move, since it's moving, what kind of energy would that be? Kinetic energy. Am I clear?
Yes, sir.
Kinetic energy. So it means that the kinetic energy of the given electron is equal to the energy supplied minus the work function. The amount of energy that it uses to move here It's going to be what? Energy supply minus one function. Does that make sense to all of us? Okay. Now, how was this kinetic energy measured? We are going to see it in a jiffy. But before we see that, now see this. We are going to see that this is going to be what? Half mv squared is equal to what? E minus phi. And phi is hf naught, right? So we know that E therefore becomes what? Half mv squared plus hf naught. Does this make sense? Okay. So if f naught is frequency and is light that is traveling, remember that frequency of light, recall that frequency is v over lambda. Equation 1, equation 2, equation 3, equation 4. Recall that frequency is what? V over lambda. And v is velocity, right? And velocity of light is what? Is c. It's denoted by c. Do you remember? So f sub naught will be c over lambda is the minimum wavelength of light that is needed. If threshold frequency, we call this one threshold wavelength. Is that okay?
Yes, sir.
All right. So it means that our equation here, what function can translate to what? H c over lambda sub naught. Does that make sense? Yes, so our equation here too can become what? Total energy equal to what? Half mv squared plus hc over lambda sub naught. Do you understand now? Equation 5. Are we good?
Yes.
Now, how was that kinetic energy measured actually? This was how the kinetic energy was measured. So they used a plate, and that plate was, the plate was put in, let's put it this way, in a tube. So they used two plates, two metal plates. One is polished, the other is not polished. So let's say this one was the one that was polished, and it was connected to a battery. Is that okay? It was connected to a battery. Let's show. Now listen, the way it was connected is very important. If the radiation of light strikes like this, where electron goes, electrons will be emitted here, right? And will move. The reason why it was put in a tube is so that there will be no interference to the outside. Is that okay? So the electrons will now move from here, right? And they'll move towards this plate, isn't it? So if the electrons are moving like this, where's the direction of conventional current? It should be like this, isn't it? So this was the way it was done. If I do it this way, well, in this system, what's the direction of conventional current? This direction, right? And the electrons are moving this way, right? Good. So by connecting it this way, we are connecting the positive plate here to the negative plate, because the negative plate is the plate that is emitting electron, isn't it?
Yes, sir.
So by connecting it like this, we are creating what is called electrode. We are creating what is called stopping potential. What is called what?
Stopping potential.
Because this is the reason. This is the reason why it was done this way. If electrons were emitted here, electrons should flow in this direction, right? If electrons are flowing in this direction, it means conventional current is this direction. But if we oppose it here, by connecting like this, it means conventional current should be like this, and electrons should flow backward, right? Right? So there is a kind of opposition here, which is what? Stopping potential. Is that okay? So we will now increase the voltage of this thing. We will increase the voltage of this guy until electrons can no longer move to this plate again. If the voltage is not high enough, because of the amount of frequency of the amount of energy that these electrons are gaining to move, there will still be movement, electricity moving in this direction. So if we increase the voltage enough, the electrons will not gain kinetic energy to move towards this plate again. They will not be able to move against this potential difference. So we'll call this potential here, we call this what? The stopping potential. Does that make sense now? So and remember that the potential energy is what? Work done per unit charge. Does that make sense? So potential energy here is going to be work done is the energy, right? And what energy are we working against? Kinetic energy. Does this make sense? Over the charge here is electrons. Does this make sense? So Ke is also giving us what? Electron volts. Do we understand? Is it clear? Yes, so ideally, we could also say that our equation from here, we turn to what? Total energy equal to what? EV plus HC over lambda naught. Are we good? So those are different forms of the formula I use to solve questions under photoelectric emission. If you don't understand the entire thing, raise your hand. Well understand, right?
I don't understand this stuff.
This one here, you don't understand it. Okay. Now, if I connect this system like this, and I place load here, if I put a load here, say a resistor, in what direction should current flow here? Positive to negative, isn't it? But if I reverse it like this, in what direction will it flow? The opposite direction, isn't it? Okay. So now watch. Let's leave it in this direction. Okay. So let's remove this battery. Let's remove this battery. We remove the battery, and our irradiated plate is like this. Irradiated means the radiation of the sun is touching it like this. Are you with me? And it's inside a tube. If our irradiated plate is here, the minimum energy that this guy needs to eject electron has been provided it, right? So electrons are already being ejected. So if the energy is more, the electrons will gain what? Kinetic energy, isn't it? So the total energy will be the minimum energy they require to get ejected. The total energy will be the minimum energy they need to get ejected plus the kinetic energy that they gain. So the kinetic energy will be used to move from this plate to this plate. So in that case, it means that electrons are flowing in which direction? This direction, right? Okay. Let's eyeball this now. Just cover this. Just assume this was not there now. Now, if I connect my battery this way, my cell this way, in what direction will electrons flow? No, from this battery, from this cell, in what direction? In this direction. Do you get it? It's convectional current, which is positive charges that move in this direction. Is it clear? So, if electrons are the one moving in this direction, and we are connecting our plate like this, electrons are moving against the direction of electrons movement here, right? So it means that they will create a potential that they need to move against here. So for them to actually be able to move, the kinetic energy all the time must be greater than the stopping potential. If the kinetic energy is still greater than the stopping potential here, they will keep moving. Is that okay? The moment we are able to give it an amount of stopping potential that is equal to the kinetic energy, there is no more movement. Electrons will stop being ejected there. Does that make sense now? So the kinetic energy will be equal to stopping potential there. All right. So, and in fact, we can generate another equation from there. So, K, we have mv squared equal to EV. So what do we do here? No, this is voltage. Oh. That's why you see capital V. This is what? Velocity. So what can I calculate here? Velocity will be equal to what? 2 times this. That will be 2EV over M. Root 2EV over M. That is what? Velocity. Do we understand?
Yes, sir.
All right. So, because it will want to move against the potential that is created here, we call it the stopping potential. All right, let's go to the next one. Now, nuclear physics, primarily. Nuclear physics. You know that, let's talk about the nucleus. Let's talk about the nucleus. Do you understand me? Pause, please. Let me see how much we have. So basically, because so I'll reiterate what I've said. I said under nuclear chemistry, we are studying the atom, the nucleus of the atom, and in the nucleus we have, the atom, the historically was first named in 400 BC. That all matter consisted of atoms, and atoms are the smallest particles, and that they were indivisible. So, and this idea was held on to until 1808. John Dalton stated the same thing, that they were indivisible, and um, around 1858, Julius Pecker. So Julius Pecker actually worked on a tube, and they called it the cathode ray tube. Cathode ray tube, and he discovered that there were emissions of radiation that were, on the other end of the cathode. Is that okay? So, and he saw that these emissions were basically, so they didn't know what to name the emission until 1897 when J.J. Thomson performed the same experiment. And although before that time, a certain Wilhelm, in 1869, William, I can't remember his name, a certain man, William, worked on the same thing and saw that they were deflected by an electrostatic field. So it was deflected towards the positive plate of an electrostatic field. So he discovered that this radiation consisted of, they were negatively charged if they were deflected towards positive plate. Okay, so it was in 1897 that J.J. Thomson now named them corpuscles. We now know them as what? Electrons. Corpuscles, but we now know them as what? Electrons. And he was regarded as one who discovered electrons because he gave a model for the atom. He was one that gave the first model for the atom about how the shape of an atom really was. Since now we know that atoms are not actually indivisible. Is that okay? So atoms, he gave the plumb body model of the atom, that the atom was a positive sphere consisting of what? Embedded negative charges. Is that okay?
Yes,
negative charges were embedded in it. Now, in the next, so that his proposition had some things that it could not really explain, such as how electrons actually were given out. Do you understand? If this whole thing was such that the electrons were held into the distance, it means that electrons may not be able to, chemical reactions that occur easily will not be able to occur if this thing were fixed into the plumb, right? Into the pudding rather. So we're like plums in the pudding. Is that okay? So this guy, Rutherford, in 1904 to 1905, with his associates, Marsden and Marsden and who? Do you remember? Okay, Marsden and a particular guy, they were the ones that all worked on it and saw that really the plumb body model was wrong, and they said that electrons were actually moving around a particular nucleus. So they discovered that there was a nucleus that was consisting of only positive charges, that comprised of only what? Positive charge. He did not see the idea of neutral charges, neutrons. Is that okay? So we regarded him as the one who discovered what? Protons. So he said that that nucleus consisted of only positively charged center and what? And how he proved that was that he told his associates, or I don't know whether he told them. I think it was he told them, because that day we went to a bar. You understand? So I was there in that bar. His lab was beside the bar. The second door like this to the right. You check the second door to the right. By the time you come out, like you enter his lab. Do you understand? So yes, that day I was there. He told his associate that, how about you try this? Do you understand? Geiger and Marsden.
Yes, I said Geiger and Marsden.
Do you understand? So he told Giga was the eldest. Do you understand? He called Giga. Giga, how are you? This experiment that I've been trying to prove this JJ Thompson wrong. How do we do it? Giga and Mazen now say, Mazen was I don't know what to do. Giga now say, sir, how about we go and bombard a gold foil, a thin, very thin, almost planar. Is that okay? A thin gold foil with alpha particles. Is that okay? So he bombarded a thin gold foil with alpha, alpha particles. So gold foil bombardment. Say gold foil bombard. Everybody. Gold foil bombard. Diggy, 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 diggy. All right, let's go. So now, that thing gold foil, they bombarded it with alpha particles or positive charges. You know, alpha particles are positively charged. Is that okay?
Yes, sir.
And so what they discovered was that there were some parts of it that were deflected. Is that okay? They were deflected. Is that okay? No, there were some that passed straight. Is that okay? And there were some that were deflected. No. Some were deflected. Is that okay? And some were undeflected, while some were repelled at the center. Is that okay? So if they were repelled at the center, it means that there were positive charges at that center that repelled those ones. Does that make sense?
Yeah.
So it was those positive charges that he named as what? Protons. Do you understand?
Yes,
he didn't have the idea of neutrons then. Do you understand?
Yeah.
He didn't have the idea of neutrons then. Then in 1932, somebody say 1932. 1932. 32. Say 32. So in 1932, a certain guy, this guy, very handsome guy, there was a day when we were in this thing, we used to be friends. You understand? What caused our fight was he borrowed my shoe, he didn't return. I had to fight him honestly. I mean, it's not ideal. How can you borrow someone's shoe and not return? So 1932, this guy, he's still my friends until today. You understand? We still chat, we still talk. You understand? But right, so James Chadwick, a certain what? He was he discovered nucleus. The day I was discovering himself, if not for me, okay, let's not talk about my own story because I don't like to put myself in the picture. Do you understand now? So he discovered what? Neutrons. I'm sorry. Discovered what?
Neutrons.
So that there was a central nucleus where there was a neutron and a proton, because that was the only classical explanation for how that the positive charges within the nucleus did not bump each other. That the negative, the neutral charges were standing in between them. But even then there's another hypothesis in nuclear physics that we'll talk about, which is the remaining two fundamental forces. Is that okay? There are two fundamental forces now that we have considered. Electric force, fundamental force of nature, there are four, right? Electrical forces, gravitational force, magnetism, electromagnetic force. Is that okay? Then the fourth one is the nuclear force. And there are two types of nuclear forces. We have the strong nuclear forces and the weak nuclear forces. So it's the strong nuclear forces that are keeping the protons together. Do you understand? In the nucleus. That's why the nucleus is not scatter. Because, positive charges cannot stay together. Right? They should what? Repel. But there is a strong nuclear force that acts at very small radii. It doesn't have to have at large radius. The radius must be very small. The distance is very small for it to act. Is that okay? And it's a very strong force. That's what is keeping the nucleus in place. Is that okay?
Yes, sir.
So, but basically, that's the history of the entire thing. So, overall, we now know that the atom comprises of, and he bombarded beryllium foil also with beta particles, I think. That guy, James Chadwick. I can't remember because I don't like him. That's why I can't remember. Is that okay? We fought. Is that okay? So, but I think it's beryllium. Nobody will ask you that in your jam. With beta particles. We fought. No, I beat his head. Let's go. I always want to know about the fight. Let's go, please. Now, in the atom, we now have three subatomic particles, right? Which are what? The protons, electrons, and neutrons. Abbreviated as what? Abbreviated as what? Now, the protons are the what? Positively charged subatomic particles. Electrons are what? Negatively charged subatomic particles. The neutrons are what? Neutral charges, right?
Yes, sir.
Okay. Now, for an atom in the ground state, the number of protons is equal to what? Is that okay?
Yes, sir.
For this in the for one in excited state, proton and neutron are not proton and electron are not equal. Is that okay? But we also know that the proton number is equal to what? Atomic. Okay, but proton plus electron plus neutron make up what? Mass number. So we say that the total mass of an atom consists in where? Is contained in what? The mass of an electron is contained where? In the nucleus. Why? Because the electron has what? Negligible mass. What's the mass of a proton? 1. What's the mass of neutron? 1. What's the mass of electron? 1 over 108, 1,850. Is that okay? Of that of protons. Is that okay? Do we remember? All right. And who this guy, he also calculated the charge to mass ratio of electron. J.J. Thomson. Is that okay? Charge to mass ratio. Is that okay? Just charge to mass ratio. Charge to mass ratio. Is that okay?
Okay, sir.
Then this guy, using oil drop experiment, R.A. Millikan. Do you remember I told you about oil drop experiment? In which year? 1915. Okay. Okay, but the point, let's just get to the major thing about nucleus. You know that proton plus neutron is what? Mass number. Are you with me?
Yes,
so now, if an atom, do atoms have the same atomic number? Are there two atoms? Is it possible for two different atoms to have the same atomic number? Yes, in the condition of what? Isotopy. Is that okay?
Yes,
e.g., we have chlorine 17 and chlorine 17, right? But both of them do not have the same number of neutrons, right?
Yes.
So this one is chlorine 35.5. This way we write it. This is called a nuclide. This is called what?
A nuclide.
A nuclide is just a structure or a formula showing the mass number and the atomic number. So chlorine 17 what? 30, is it 37 or 37.5? 37, good. Now that is isotopy. So these two are called what? Isotopes. They are called what?
Isotopes.
Now there is also isobar and there is also isotones, right? Now what are isobars? Isobars are the ones that have the same, isotones have the same neutrons. So isobars we have the same mass number but different atomic number. Isobars have what?
Same mass number, different atomic number.
Okay, so equal mass number. E.g., we have oxygen is 18, right? Which other one is 18? Oxygen is 18 and 16, right? Those are two isotopes. There is oxygen 16 and there is oxygen 18, isn't it?
Yes.
Now, this oxygen 18 is similar to, there is carbon 14. Okay, there's carbon 12, right? And carbon 14. Good, I've seen one now. So there's nitrogen what? 14. So this will be an isobar of this. Does that make sense?
Yes.
This will be what? This will be what? Isobars. Okay. For isotones. Okay, let's combine all what we have. If this one is 18, which other guy is 18? We have chlorine, and fluorine is 19. Before fluorine is what? Oxygen, right? Oxygen, fluorine. Is there fluorine 18? Fluorine 19 is all we have now. Maybe there is fluorine 18. If there was, Watch. If there was, this guy is going to be different atomic numbers, right? I'm talking about isotopes now. Isotopes, are you with me? They have different atomic numbers. Is that okay? No. Isotopes are equal in only neutron numbers. They have equal number of neutrons. Is that okay? For example, for that oxygenating now, what's the number of electrons it has? Number of proton it has? 8, right? What's the number of neutrons it will have? If you don't understand how to do that, raise your hand. You understand, right? The number of proton is 8, which is the atomic number. So the number of neutrons to have is 10. Which other guy can have that same guy? Fluorine 19. Does that make sense? We subtract. How many neutrons does he have? 10. Do you understand now? So the concept of isotope. Do you see what the concept of isotope destroyed the idea of isotopic, destroyed the idea of atoms of the same element, of different element are, or atoms of the same element are, what's it called? One of Dalton's atomic theory anyway, is that okay? That said that atoms of the same element are always equal. Is that okay? So isotopy destroyed that phenomenon, that idea. Is that okay? So that's isotope. What is isotope? Same what? Same neutron, but different mass and proton. Is that okay?
Yes,
but this one, same mass number, different proton. Is that okay?
Yes, sir.
All right. Are we good?
Yes, sir.
So now let's now go to what is this guy about. This nuclear chemistry, nuclear physics rather. Now you know, so in 1896, you know that 1889, those years, 1887, who? Hertz, right?
Yes, sir.
1897, who? J.J. Thomson. What did he discover? Electrons. Now, 1896, a year before that time I was still in, was it primary 6, I think. I was still in primary 6 then. At that time, we used to, that time, J.J. Thomson, he was a fine guy, but this was the problem. The problem was that he had this thing in his ear. At this side of his ear, it's only me that I saw that, I knew that thing. Because it was only me he talked to it about. I was the only friend he could confide in. Do you understand what I'm saying? I was the only one he could tell the situations of his life. Do you understand? I was the only one he could explain situations to. And he said, my friend. I said, yes, my friend. He said, my friend, do you know I have something? I said, yeah. Okay, let's go to what happened. Now in 1896, a certain guy, Henry Becquerel, this guy, I'll tell you a story. He likes me a lot, eh? Say Henry Becquerel. Henry Becquerel. What is Becquerel? Henry Becquerel. Becquerel or Becquerel? Becquerel. Becker. That was the song we used to sing for him then, and he liked it. I composed it for him then. So Henry Becquerel was the first person to discover the phenomenon of radioactivity. And what did he study? He saw this guy, pitch blende, right? Yeah. Pitch blende, which was the organic form of what? Uranium. Is that okay?
Yes, sir.
Which uranium is pitch blende? Uranium 238. Is it 234 238? I think it's 238. I can't remember. Okay, so uranium 238, which was pitch blende, he saw that it emitted a particular radiation. Is that okay? And because of that, he called the phenomenon radioactivity. Was it the one named radioactivity or Marie Curie? I think it's Marie Curie, but he was the first person to discover the phenomenon. Is that okay? Yes, so Marie Curie, those two boys, those two, the husband and wife, yeah. I was the one when they were dating, for example. This is what happened. There was one day on Saturday. You know the roof of their house, that side. You know, what's it, please? You know that was So that was how I killed them. I did what? pitch blend, air becquerel. So then in 1898, these two girls, this boy and girl, they came to me, they said they wanted to marry each other. And they married in 1 year, like I think they married around 1890 something. So when they married, in their marriage, they were both chemists. Is that okay? They were both chemists. And that day I told them, don't marry this girl because it might cause her death, this thing that she's exploring. Do you understand? It was eventually, it happened that it was this radioactivity that still killed her. She died of cancer. Honestly. Life, right? Because I was telling this guy, their names were Mary and Pire Kuri. Do you even hear the name? Kuri. Like Kuri. See. Are you with me? So in 1898, both of them, they investigated which two atoms, which two guys, polonium. She was the one that actually named it polonium and I advised her to do so because she discovered it. So she now came to me and said, Master, Mary now, who is this? Mary and Pierre. Did you not do PhD? Monso, Baro, Pierre, de Coubertin. PhD. Okay. So polonium, because she was from what? Poland. Both of them, they are what? From Poland. And I told them, okay, name it after your country. Is that okay? Yes, sir. So you now named it polonium and what are the two? That's the second guy. Polonium and what? Thorium. Radium, right? Radium, thank you. Radium. All right. So this was the case. So they discovered that these guys too were also what radioactive. And in 1910, she won a Nobel Prize. I told them to give her. You understand? I told them to give her that so that me. You see that thing? I don't used to be proud. You understand? I know it's bad because in his life he must be humble. 1910. All those times, everybody was collecting award. Me, I didn't want to collect because I said, if I go and collect now, people start studying me. Just that's why we are investigating into their private lives. I didn't want to. You should know when to. So come now, see. All right. So that's the case. And so we discovered that there were three types of radiation that were discovered. Is that okay? I will call them alpha, beta, and gamma radiations. Is that okay? Yes, sir. Now, so it was such that if the radioactive material was here, we saw that, and we put an electric field there, or a magnetic field. We saw that this guy, there's one that is deflected a lot towards the positive, and there's one that is deflected weakly towards the negative, and there's one that was deflected that was not deflected at all. Is that okay? So we call this a photographic plate. Is that okay? Yes, sir. Now this one that is not deflected at all is what? Gamma. It was the strongest. You understand? That guy, very strong guy. Basically, gamma is not a guy. Alpha, beta, gamma simply means the first letters of the alphabet. I've told you. You know it's ABC. Alpha, beta. Is that okay? We know in Greek alphabet, alpha, beta, gamma, delta, epsilon. Just now. All right. So this thing simply means first type of radiation, second type of radiation, third type of radiation. No. Under radioactivity, there are just these three. Is that okay? Yes, sir. Right. So now for alpha, no, not like they are just these three, because if you see other particles such as neutrino, you've not seen neutrino before. Positron. You've not seen neutrino before. Positron emission. Cholu. Neutrinos. Positron. You've seen it, right? Positron is positive electron. Anyways, leave that one for now. Electron is negative, right? Yes, there's positive electron. We'll talk about it later. Now look at this. In chemistry, when we get to nuclear chemistry, because we don't really do much on this here. So this guy is also deflected towards the north. The positive is the north, right? Yes. acts like the north, or north acts like the positive, and this one is the what? The south in the magnetic field. Do you understand? So they subjected them towards these two fields, and bless you, and they were deflected like this. Now this one that is really deflected towards the positive is the what? Beta radiation is the what? And the one that is weakly deflected towards the distance is what? Gamma alpha radiation. Do you understand now?
Yes, sir.
The alpha is weakly deflected towards the negative. Are you with me?
Yes, sir.
While the beta is strongly deflected towards the positive plate. Break that down. So it's strongly deflected towards the positive plate. And one of these ones is really deflected because this one is heavier than this guy. Do you understand? Alright. What's the mass of the electron? So let's talk about their properties. That's what you understand now. The mass of the electron we said is 0, old people. We said is what? Why the atomic number? -1. Do you remember? So let's talk about their properties now. So we have the alpha, beta, gamma. Are you with me?
Yes.
So let's talk about their nature. Now these ones are basically helium nuclei. Is that okay?
Yes.
The helium nuclei, the alpha rays, they are the helium nuclei. These guys are what? Fast moving streams of electrons. Is that okay?
Yes.
They are electrons. Why this one? Gammas. They are what? Basically what? EM waves. Is that okay? So because they are waves, they are what? Undeflected. Are you with me?
Yes.
Now these ones, they have what is called high ionization energy, high ionization effect, high ionization effect, high ionization effect. Why these guys? They have what? Moderate ionization effect. Is that okay?
Yes.
But this one, they have what? Weak or no ionization effect. Low, yeah, okay, yeah, low. Very low, not just low, very low. Very low what? Ionization effect. Are you with me? Now let's talk about their penetration power. Which one has the highest penetration power? This one has the weakest penetration power. Why is it weakest? Because it has the highest ionization. No, not because of that. But basically, the higher the ionization effect, the lower the penetration power. That's why this one can be stopped with what? A piece of paper, right? Then this one has what? Moderate what? Or moderately long. Is that okay? Weak penetration power. Moderate penetration power. It can penetrate about 100 centimeter. Do you understand? It can go, the distance can travel about 100 centimeters, but it can only penetrate, it can be stopped by aluminum sheet. Is that okay? Then this one can penetrate about tens of thousands of centimeters. Is that okay? So highest penetration power belongs to this. Highest ionization effect belongs to, do you understand? All right. Then the speed. How about their speed? This guy what? 10% of speed of light. This one is what? 90% of speed of light. And this one is what? Equal to speed of light. Are we clear? And what speed of light serve you? Are we good?
Yeah.
So over time, many studies went into this field and they discovered what is known as radioactive disintegration. Radioactive what? It is also known as decay. It's also known as what? Decay. Radioactive decay. And they discovered that it happened over time. Do you understand? It was measurable. The time over which a particular radioactive element decayed was measurable. Is that okay? They discovered it was what? Measurable. And they measured it by what we call the half-life. They measured it by what is called what?
Half-life.
Okay. Is one of the use of this decay is the carbon dating technique. Is that okay?
Yes.
They use the half-life of carbon-14 to do radioactive carbon dating on human or anything on fossils. Is that okay? All right. So, because there's a deposit of carbon-14 in us, in humans, in substances, is that okay? And this carbon-14 begins to disintegrate when the animal dies. Do you understand? Right, so half life. Somebody say half life. You say half life. You say life. Now, the half-life of a substance is the amount of time it takes half of the starting mass to disintegrate, or the amount of time it takes a substance to disintegrate to half its original amount. The amount of time it takes half of a substance, or half of the starting mass of a substance to disintegrate, or the amount of time it takes a substance to disintegrate to half of its starting mass. Am I clear?
Yes, sir.
That is what
Half-life.
somebody say half life.
Half-life.
Half life. Half life T half is given by T half. Is that okay?
Yes,
it's
sir.
given by ln 2 over lambda. Am I correct? No.
Yes, sir.
Is this correct? Verify this for me.
Yes, sir.
Okay. So T half, this lambda is given by or K in some textbooks you see K. Is that okay? It means lambda or K means what? Decay constant. Somebody say decay constant. Decay constant. Alright, so T half is now giving us, what is this guy? 0.693 over lambda. Over, so that lambda or decay constant is also equal to 0.693 over T half. Do you understand?
Yes, sir.
Now, let me give you a question. If you are told a certain substance, 200, let's say it says 200 grams of a particular element has a half-life, 200 grams of a particular element, which has a half-life of 50 days, for example, to disintegrate. Are you with me? How many will remain after 1,000 days? How much will remain after 1,000 days? Very simple. Do you know what you do? You disintegrate it when you get to what? 1,000 days. Ha! That's so much, but let's try it. Is that okay? So from 200, it will disintegrate to half of its mass, right? What is half of its mass? 100. In how many days? Let's not do that yet. Let's still keep disintegrating it. This one will disintegrate to what? 50. This one is what? This one is what? This one is what? I'm not doing it again. Let's choose. No. Okay, God bless you. This one will go to what? 3.125. This one will what? 1.5625. 5625. Let's see it. 1, 2, 3, 4. 200. Jesus Christ. Let's stop. Let's stop at 500 days. Is that okay? After 500 days, how much will remain? Okay, so we have 50 days, 50, 150 years, 150 here, 200 days, 250 days, 300 days, 350 days, 0.78125. Here we are 350 here, right? 39065.
0.195.
All right, look here, let's start. So 350 at here to abbreviate by how many days? 400 here, 450 here, 500. So after 500 days, this is the amount that what remain. So what amount would have disintegrated? You now subtract this from 200. I'll give you what? 199.804, whatever. Is that okay? Yes, are you with me?
Yes, sir.
This is the amount that would have what? Disintegrated. But what amount will be left?
0.195
grams. Are you good?
Yes,
now let's take the last part of this thing. The last part is about, we talked about the fact that in quantum mechanics now we have discovered that it means that particles can take waveform. There is some certain entities, what I call entities, have particulate and wave natures, wave-like natures. Matter can have particulate and wave-like nature. Is that okay? So we call it the wave particle duality. The wave what?
Particle duality.
You know, it was this guy. So the idea started from that photoelectric effect. Is that okay? And that was why some scientists did not have this thing. They did not agree about this thing. That how can something be wave and still be a particle? Is that okay? You know, if it's particle, it means it has mass. Does that make sense? So we discovered from photoelectric effect that what light has what mass and what light has what mass and was also what a wave. Is that okay? So in its particular nature, it takes what is called what photon, which is the what energy what packet of light, energy packet of what
Light.
or packets of light, packet of quantum of light. Is that okay? Okay. Now. So so the theory of this thing, this wave particle duality could only be proven by some, I think about 3 or 4 phenomena. I can't remember all, but I think I remember that photoelectric effect. Is that okay? And what was this thing that we said proved it? That in classical mechanics, we said that if you increase frequency of light, what should happen to the energy that is contained? Energy should be given to the high amount of energy should be given the electrons, right?
Yes.
But it did not happen like that, right?
Yes.
Okay, so we now discover that light actually travels in small packets known as what? Photons. So is the photon of energy, photon of light that carries just the amount of energy that guy can use to escape the surface of the metal. Is that okay?
Yes.
So in photoelectric we saw that. Then there's also something called the Compton effect. The Compton effect. Now, about the Compton effect, you guys will leave the explanation of that in the comment section. I can't remember what it is. Is that okay? Compton effect. There's also something about the we have photoelectric effect, Compton effect, forgot the meaning of these things. So, did I teach you wave particle duality last time? No, right? Okay, but basically, I probably gave you. I thought you were asking Heisenberg's uncertainty principle, right?
Yes.
Heisenberg's uncertainty principle, quantum number. So Heisenberg's uncertainty principle states that so in physics, the principle is such that it was impossible to determine the exact position of an electron as well as the momentum of that of a particle, rather the exact position of a particle as well as the momentum of the particle simultaneously. Is that okay? That is impossible to do what? To determine the exact position and momentum of what? Simultaneously, yes. And he now further said that the probability, are you with me?
Yes, sir.
The product of the uncertainty of position and the uncertainty of the momentum is represented by P, right? That is always greater than the Planck's constant. Does this make sense? In some distance, you see 2 pi because they are referring to orbits. Is that okay? What is an orbit? The path taken by what? Electrons, right? Or basically particles too. You understand? And it's concentric. So we're using 2 pi, which is 360 degrees. Does that make sense? So yes, it's greater than or equal to this. Do you understand now? So if you are given a formula, a question, you can say change in x times what is changing this? Changing what? What is momentum? Formula for momentum. Does that make sense? Will be greater than or equal to h over 2 pi. Do we understand? All right. So by the time you have all of these formulas, when you see a question, you will know what to apply. Is that okay? Just master it. With this, there's another scientist that worked on this. See, I will not be talking about what he did. De Broglie. Is that okay? I think his work, we usually study his work more in chemistry than what we do in physics. Now, with this, we come to the end of physics end game. A round of applause for yourselves, Then secondly, a round of applause for those that have watched until this time. So, right. So for those that stuck with us till day 5, what do we say to them? Amen. A round of applause for the teacher too.